Look up at the night sky, and you're seeing a snapshot of the cosmos, a picture that seems timeless and permanent. But what if that picture was moving, and not in a slow, gentle drift, but in a frantic, runaway rush? What if I told you the universe isn't just expanding, but that this expansion is accelerating, driven by a mysterious force we don't understand? Every galaxy, every star cluster, every bit of space between them is being pushed apart faster and faster with each passing moment. This isn't science fiction. It's the startling reality uncovered by astronomers just a few decades ago. It upends everything we thought we knew about cosmic evolution and points toward a future for the cosmos that is both spectacular and, in many ways, deeply unsettling. This incredible phenomenon is governed by the expansion rate of the universe, a number scientists call the Hubble Constant. It's more than just a figure in a textbook. It's the key to unlocking the history and ultimate fate of everything that exists. For nearly a century, we've known the universe is growing, but the discovery that this growth is speeding up was a shock that earned a Nobel Prize. It means something is actively working against the pull of gravity, something invisible and pervasive that we've named dark energy. This single finding has thrown modern cosmology into a beautiful crisis, forcing us to reconsider the very laws of physics and the nature of reality itself. So, how do we measure something as vast as the expansion of the entire cosmos? What does this accelerating expansion mean for the distant future of galaxies, stars, and even the fabric of spacetime? And what exactly is this dark energy that appears to dominate our universe? You're about to embark on a journey through 30 mind-bending facts that will guide you through the greatest detective story in science. We will explore how we measure the unmeasurable, grapple with the implications of a runaway universe, and confront the profound mystery that lies at the heart of it all. This is a journey to the frontier of human knowledge, and it promises revelations that will forever change how you see the cosmos and our place within it. And so we arrive at our first and perhaps most staggering fact. The universe is not just expanding, it is accelerating. This isn't a gentle, coasting growth like a ball rolling on a flat surface. It's as if that ball has been pushed and is now rolling faster and faster down a hill, defying all our basic expectations. For decades, the prevailing wisdom was simple. After the Big Bang set everything in motion, the collective gravitational pull of all the matter in the cosmos, every galaxy, every star, every speck of dust, should have been acting like a cosmic brake, gradually slowing the expansion down. The biggest question for astronomers was whether there was enough matter to eventually halt the expansion and pull everything back in a big crunch, or if the universe would just keep coasting outward forever at an ever-slowing pace. The answer, when it came in 1998, was neither. Two independent teams of astronomers were using distant stellar explosions, called Type 1, a supernova, as cosmic mile markers. These supernovae are incredibly useful because they all explode with roughly the same intrinsic brightness. By measuring how bright they appear from Earth, astronomers can calculate their distance with remarkable precision. Simultaneously, by analyzing the light from these explosions, they can determine how much the universe has stretched since the light began its journey billions of years ago. What both teams expected to find was that the most distant supernova, those whose light left them when the universe was much younger, would appear brighter than expected, showing that the expansion was slower back then, just as a decelerating universe would predict. Instead, they found the opposite. The faraway supernovae were significantly dimmer. This could only mean one thing: these ancient stellar explosions were much farther away than anyone had calculated. The universe wasn't just expanding. It was expanding faster now than it was in the distant past. The expansion rate was increasing. The reaction in the scientific community was a mixture of profound shock and deep skepticism. The finding was so bizarre, so counterintuitive, that many scientists initially believed there must be some mistake, perhaps interstellar dust dimming the light or an unknown flaw in the supernova measurements. But as more data poured in from different instruments and methods, the conclusion became inescapable. The acceleration was real. This monumental discovery earned team leaders Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. To explain this bizarre phenomenon, cosmologists were forced to propose the existence of a mysterious, repulsive force permeating the very fabric of space. They called it dark energy. Think of it this way: if gravity is the force that pulls everything together, dark energy is the force that pushes everything apart. And it's not a weak force. Measurements now suggest that dark energy makes up about 68% of the total energy content of the entire universe. It is the dominant component of reality, and we have almost no idea what it actually is. It's the ultimate cosmic irony. We've given a name to our own ignorance, to the force that is actively shaping the destiny of the cosmos, while remaining completely invisible and undetectable by any direct means. This single fact, the acceleration of the universe's expansion, didn't just add a new chapter to cosmology. It tore up the old textbook and forced us to start writing a new one from scratch. Just a few decades before the discovery of the accelerating universe, our entire cosmic perspective was turned on its head by a single, meticulous astronomer. For centuries, the prevailing view, reinforced no less by the great Albert Einstein himself, was that the universe was static, eternal, and unchanging. The Milky Way was thought to be the entirety of the cosmos, an island of stars floating in an infinite, empty void. This comforting notion of permanence was shattered in 1929 by the work of Edwin Hubble at the Mount Wilson Observatory. Using the most powerful tool of its time, the massive 100-inch Hooker telescope, Hubble was painstakingly observing faint, fuzzy patches of light, then known as spiral nebulae. He was building on the work of astronomers like Vesto Slipher, who had noticed that the light from most of these nebulae was shifted toward the red end of the spectrum, a phenomenon known as redshift. While redshift can be caused by motion, its true cosmic significance was not yet understood. Hubble's genius was to combine these redshift measurements, which indicate velocity, with actual distance measurements to these objects. But how do you measure the distance to something so impossibly far away? Hubble used a special class of stars known as Cepheids variables. These are stars that pulse with a regular rhythm, and crucially, the period of their pulsation is directly linked to their true intrinsic brightness. It's like having a light bulb where you can tell its wattage simply by timing its flicker. By finding these cosmic lighthouses in the spiral nebulae, measuring their pulse, and noting how dim they appeared from Earth, Hubble could calculate their distance with unprecedented confidence. The results were nothing short of earth-shattering. Those spiral nebulae were not part of our Milky Way. They were entire galaxies in their own right, vast islands of stars millions of light-years away. We lived in a universe filled with galaxies, but the real revolution came when Hubble plotted the distances of these galaxies against their velocities, derived from their redshifts. He found a stunningly simple yet profound relationship. The farther away a galaxy was, the faster it appeared to be receding from us. A galaxy twice as far away was moving twice as fast. A galaxy 10 times more distant was racing away at 10 times the speed. This direct proportionality between distance and velocity is what we now call Hubble's law. This wasn't just a random observation. It was the smoking gun. The entire fabric of space itself was stretching, carrying the galaxies along with it. The redshift wasn't because galaxies were simply moving through space like rockets, but because the space between us and them was expanding, stretching the wavelengths of light as it traveled toward us, making it redder. This single graph, this linear relationship, was the first direct evidence for the expansion of the universe, the aftermath of the primordial event we now call the Big Bang. Einstein himself visited Mount Wilson and, upon seeing the evidence, famously called his earlier introduction of a cosmological constant to force a static universe his greatest blunder. Hubble's work had irrevocably transformed our cosmos from a small, static island into a dynamic, expanding arena of unimaginable scale, setting the stage for every cosmic discovery that would follow, including the ultimate shock of its acceleration. But if the universe is expanding, the next logical question is a simple one: how fast? This brings us to the very heart of the measurement, a single, crucial number that astronomers have been trying to pin down with excruciating precision for nearly a century. It's called the Hubble Constant, symbolized as h0, and it is quite literally the current expansion rate of our entire cosmos. Think of it as the universe's current speedometer reading. The way we express this speed, however, can sound a little strange at first. The Hubble constant is measured in kilometers per second per megaparsec. Let's unpack that. A megaparsec is an almost unimaginable unit of distance, equivalent to about 3.26 million light years. So, what this unit means is that for every additional megaparsec of distance between us and a distant galaxy, that galaxy appears to be receding from us faster by a certain number of kilometers every single second. To put some real numbers to it, one of the leading values for the Hubble constant today is around 70 kilometers per second per megaparsec. This means a galaxy that is exactly 1 megaparsec away from us is speeding away at 70 kilometers per second. A galaxy twice as far, at 2 megaparsecs away, is receding at 140 kilometers per second, and a galaxy 10 megaparsecs distant is racing away at a staggering 700 kilometers per second. This isn't because these galaxies are somehow propelled through space with their own engines. It's because the very fabric of space between us and them is continuously stretching, and the Hubble constant is the measure of that stretch's current intensity. It's the number that quantifies how much faster the cosmic race is getting with every new inch of track that appears. You might wonder why nailing down this one number is considered one of the most important and frustrating quests in all of modern cosmology. It's because the Hubble constant is so much more than just a speed limit sign for the cosmos. This single value is a gateway into the universe's past, present, and future. By knowing how fast the universe is expanding now, we can essentially run the cosmic film in reverse, calculating backwards to determine the precise moment when everything was condensed into a single point, the age of the universe itself. A higher Hubble constant implies a faster expanding, and therefore younger, universe. A lower value suggests a more leisurely expansion and an older cosmos. So, the quest for the Hubble constant is fundamentally a quest to answer the most basic of questions: how old is everything? But the plot thickens considerably because the Hubble constant also acts as a critical key for unlocking the contents of the universe. The precise rate of expansion is determined by a tug of war between the inward pull of all matter, including the dark matter we can't see, and the outward push of dark energy. By measuring the constant with extreme accuracy, we can weigh the cosmic competitors in this struggle and determine the exact recipe of our universe. This is where the story takes a dramatic and thrilling turn. For decades, astronomers have been using two powerful but completely different methods to measure the Hubble constant, and they are getting two consistently different answers. This isn't a small, negligible discrepancy that can be brushed aside as a rounding error. This is a significant, persistent disagreement that has grown into a major crisis in cosmology, poetically dubbed the Hubble tension. On one side, we have the early universe method. This involves looking at the oldest light we can see, the cosmic microwave background radiation, which is a fossilized glow from when the universe was just 380,000 years old. By using our exquisite understanding of cosmic physics to model how that infant universe should have evolved into the one we see today, we can predict what the Hubble constant should be. This method points toward a value of about 67 kilometers per second per megaparsec. On the other side, we have the late universe method. This is the modern incarnation of Hubble's original technique, using a cosmic distance ladder built with brilliant standard candles like Cepheid variable stars and Type 1, a supernovae, to measure the distances and recession speeds of galaxies in our contemporary local universe. This method, refined with incredible precision by the Hubble Space Telescope and other observatories, consistently gives a higher value, around 73 kilometers per second per megaparsec. The universe, according to these local measurements, appears to be expanding about 9% faster than our best models of the early universe predict it should. This discrepancy is a 5-alarm fire for theoretical physics. It strongly suggests that something is missing from our standard model of cosmology. Perhaps dark energy isn't constant, but is changing over time. Maybe there is a new, unknown type of subatomic particle flooding the cosmos, or perhaps our understanding of gravity itself needs a fundamental revision. The Hubble constant, this single, deceptively simple number, has become the focal point of one of the greatest puzzles in science, a mystery that promises to lead us toward a deeper and more complete theory of reality. Measuring the vast emptiness of space requires a tool as grand and intricate as the cosmos itself, and that tool is what astronomers call the cosmic distance ladder. You can't simply stretch a tape measure from Earth to a distant galaxy. Instead, scientists have built a brilliant chain of interlocking methods where each technique unlocks the next, allowing us to climb from our own solar system out to the very edge of the observable universe. This ladder is absolutely fundamental because every single statement we make about the scale of the cosmos, from the age of the universe to the reality of its acceleration, rests upon the sturdy rungs of this carefully constructed measurement system. The first rung on this ladder, the one we plant firmly on Earth, is a concept called stellar parallax. It's a method with ancient roots, and it's beautifully simple in principle. Hold your finger up in front of your face and close one eye, then switch and close the other. You'll see your finger appear to jump back and forth against the background. That apparent shift is parallax. Astronomers do the exact same thing, but on a cosmic scale. They observe a nearby star at one point in Earth's orbit around the Sun, and then wait 6 months and observe it again from the opposite side of our orbit. The star appears to shift its position slightly against the backdrop of much more distant stars. By measuring this tiny angular shift and knowing the diameter of Earth's orbit, we can use basic trigonometry to calculate the star's distance with superb accuracy. This is our most direct method, but it has its limits. As stars get farther away, that parallax shift becomes infinitesimally small, vanishing into the noise of our measurements. With this technique, we can confidently map stars out to a few thousand light years, which is like meticulously surveying your own neighborhood, but no further. To reach beyond our galactic backyard, we need a brighter, more powerful beacon. This is where the second crucial rung of the ladder comes into play: Cepheid variable stars. These are not your average, steady burning stars. Cepheids are colossal, aging stars that rhythmically pulse in size and brightness over a period of days or weeks. In the early 20th century, the astronomer Henrietta Swan-Leavitt made a discovery that would change cosmology forever. While studying hundreds of these variable stars in the small Magellanic Cloud, she noticed a clear and powerful pattern. The brighter a Cepheid star intrinsically was, the longer its pulsation period. This period-luminosity relationship was a monumental breakthrough. It meant that by simply timing the flicker of a Cepheid variable, by measuring its pulse, astronomers could determine its true inherent brightness. It's like finding a population of light bulbs where you can know their exact wattage just by how fast they dim and brighten. Once you know the true wattage of the bulb and see how dim it appears in the sky, you can calculate exactly how far away it must be. Cepheids are brilliant enough to be spotted in other galaxies, allowing astronomers like Edwin Hubble to make the first measurements to the Andromeda galaxy and prove the existence of galaxies beyond our own. They are the crucial bridge, the intermediate step that connects the local parallax measurements to the vast expanse of intergalactic space. For the final, most spectacular leap across billions of light years, we need the ultimate standard candle, a cosmic explosion so uniform and so brilliant that it can be seen across the observable universe, the Type 1a supernova. These events occur in a specific binary star system, where a dense white dwarf star steals material from a companion. When the white dwarf reaches a very specific, critical mass about 1.4 times the mass of our Sun, it can no longer support its own weight and undergoes a runaway thermonuclear explosion. Because this trigger mass is always the same, the resulting explosion always releases nearly the same amount of energy, shining with a consistent, peak intrinsic brightness that can outshine an entire galaxy. When astronomers spot a Type 1a supernova in a distant galaxy, they know with remarkable confidence how bright it truly is. By measuring how dim it appears from Earth, they can calculate the immense distance to its host galaxy. It was precisely these monumental explosions that revealed the shocking acceleration of the universe's expansion. The cosmic distance ladder, from the local geometry of parallax to the steady pulse of Cepheids, and finally to the stellar fireworks of supernovae, is a chain of reasoning that allows us to measure the unmeasurable, providing the definitive proof that we live in a dynamic, expanding, and accelerating cosmos. While we often think of stars as constant, unwavering points of light, some of them are actually cosmic lighthouses, flashing with a dependable rhythm that makes them invaluable for navigation across the vast gulfs of space. These are the Cepheid variable stars, and they are truly the workhorses of the cosmic distance ladder. Unlike the explosive, one-time fireworks of a supernova, Cepheids offer a steady, repeating signal that astronomers can observe and measure time and again. What makes them so special is a beautifully simple physical property. The longer it takes for a Cepheid to complete one full cycle of brightening and dimming, the more intrinsically luminous it actually is. This direct connection between a star's pulse and its power is known as the period luminosity relationship, and its discovery was one of the most pivotal moments in the history of astronomy. This revolutionary insight came not from a famous professor at a prestigious university, but from the meticulous work of a brilliant astronomer named Henrietta Swan Leavitt. In the early 1900s, Leavitt was working at the Harvard College Observatory as one of the Harvard computers, a group of women who painstakingly analyzed photographic plates of the stars. Her specific task was to study variable stars in the Small Magellanic Cloud, a small satellite galaxy of our Milky Way. Because all the stars in this cloud are roughly the same immense distance from Earth, she could make a critical assumption. Any differences in their apparent brightness were due to their actual, intrinsic differences in luminosity, not their distance. As she cataloged the Cepheids, she noticed a clear and stunning pattern. The stars that took longer to pulse were consistently brighter than those with quicker cycles. She had discovered a cosmic ruler. By simply timing a Cepheid's heartbeat, an astronomer could determine its true wattage, and then, by seeing how dim that known wattage appeared from Earth, they could calculate exactly how far away it was. It's difficult to overstate the importance of this discovery. It gave us the first reliable method for measuring distances to objects far beyond our own galaxy. Armed with Leavitt's powerful new tool, Edwin Hubble made the observations that would forever change our cosmic address. In the 1920s, he pointed the massive Hooker telescope at the Great Spiral Nebula in Andromeda, a faint, fuzzy patch in the sky. He searched for and found Cepheid variables flickering within its spiral arms. By measuring their pulsation periods, he used Leavitt's relationship to determine their true brightness and then compared that to their faint appearance. The calculation was undeniable. Andromeda was nearly 1 million light-years away, far outside the known boundaries of our Milky Way. In a single stroke, Hubble proved that our universe was not a single galaxy, but a universe of galaxies. Those spirals in the sky were not nebulous clouds within our own cosmic island. They were entire islands of stars in a vast cosmic ocean. This was only the beginning. Hubble then went further, combining these Cepheids to measure distances to many other galaxies and comparing those distances to the redshifts Vesto Slipher had measured. This was the final piece of the puzzle that revealed Hubble's law and the expanding universe. Without the steady, predictable pulse of Cepheid variables serving as our fundamental mile markers, we might have remained in the dark about the true scale and dynamic nature of the cosmos for decades longer. They remain a cornerstone of modern cosmology, the essential calibrators that allow us to extend our measurements from our galactic neighborhood out to the most distant supernova, continuing to refine our understanding of the universe's accelerating expansion. Now, let's turn our attention to the most powerful and decisive tool in the cosmic distance ladder, the one that delivered the shocking news of our runaway universe, the Type 1, a supernova. Imagine a stellar explosion so brilliant, so cataclysmic, that for a few brief weeks, it can outshine the combined light of billions of stars in its host galaxy. These are not just any stellar deaths, they are precision-calibrated cosmic bombs, and their unique consistency is what makes them the gold standard for measuring the deepest reaches of space. A Type 1, a supernova, begins its life in a binary star system, a cosmic dance between two stars. One of these stars is a white dwarf, the incredibly dense, Earth-sized core of a star like our Sun that has exhausted its nuclear fuel and collapsed. This white dwarf has a very specific and dangerous goal. It voraciously pulls hydrogen gas from its companion star, siphoning material onto its surface. With every bit of stolen matter, the white dwarf grows more massive, inching toward a critical threshold known as the Chandrasekhar limit. This limit, about 1.4 times the mass of our Sun, is the point of no return. A white dwarf is supported against its own gravity by a quantum mechanical effect called electron degeneracy pressure. Up to that 1.4 solar mass limit, this pressure can hold the star up. But the instant it reaches that precise mass, the pressure can no longer counter the immense gravitational squeeze. The core becomes unstable, and temperatures skyrocket to billions of degrees, igniting runaway carbon fusion in a fraction of a second. The entire white dwarf is torn apart in a thermonuclear fireball of unimaginable ferocity. Because this detonation always happens at the same trigger mass, the amount of radioactive nickel-56 created in the explosion is almost identical from one event to the next. This nickel decays and powers the brilliant light show, meaning every Type 1, a supernova, erupts with nearly the same peak intrinsic brightness. This is the magic key. In cosmology, if you know the true intrinsic brightness of an object, its absolute magnitude, and you measure how dim it appears from Earth, its apparent magnitude, the difference between the two gives you its distance with incredible accuracy. Type 1, a supernova, are the ultimate standard candles, visible across billions of light years. This incredible reliability set the stage for one of the most profound discoveries in modern science. In the late 1990s, two independent teams of astronomers were using these supernovae to tackle what they thought was a straightforward question: how much is the expansion of the universe slowing down due to gravity? The High-Z Supernova Search Team, led by Brian Schmidt, and the Supernova Cosmology Project, led by Saul Perlmutter, were both meticulously scanning distant galaxies, searching for these telltale flashes. It was a massive international effort, like a cosmic scavenger hunt. When a candidate supernova was found, they would use the world's most powerful telescopes, including the Hubble Space Telescope and ground-based observatories in Chile and Hawaii, to measure its light curve, how it brightened and faded, and its redshift. They were looking deep into the past, observing supernovae that exploded when the universe was half its current age. The prevailing model predicted that the gravity of all the matter in the cosmos was putting the brakes on expansion. They expected to see that the most ancient, distant supernova would appear brighter than their redshifts suggested, because in a decelerating universe, objects were closer together in the past, meaning the light from those older explosions wouldn't have to travel as far through expanding space as a constant expansion would imply. But the data told a completely different, bewildering story. The distant supernovae were not brighter, they were consistently dimmer. After years of painstaking observation and re-checking for potential errors, like interstellar dust dimming the light or evolutionary changes in the supernova themselves, the conclusion was inescapable. The dimness meant these ancient stellar explosions were farther away than anyone had predicted. The only possible explanation was that the universe had expanded more in the second half of its life than anyone had dreamed. Instead of slowing down, the expansion was speeding up. The two teams, initially competitors, found their results converging on this shocking, universe-altering conclusion. They announced their findings almost simultaneously in 1998, throwing the world of physics into an uproar. The expectation of a cosmic deceleration had been so ingrained that this result was met with deep skepticism. But as more data confirmed the finding, it became clear we were witnessing a fundamental new feature of reality. The universe wasn't just expanding, it was being pushed apart by a mysterious, repulsive force, a discovery that would earn the team leaders the Nobel Prize and force a complete rewrite of our cosmic history books. This persistent disagreement between our two primary methods for measuring the expansion is not just a minor discrepancy, it's a full-blown crisis in cosmology that we call the Hubble tension. Imagine you had two incredibly precise watches, both built by master craftsmen, but one consistently runs a few minutes faster than the other. At first, you might assume one is simply wrong. But what if, after years of checking, you are absolutely certain that both are functioning perfectly according to their design? The only remaining conclusion is that there's something fundamental about the nature of time itself that you don't understand. That's precisely the situation cosmologists find themselves in today. We have two exquisitely precise methods for reading the universe's speedometer, and they are giving us stubbornly different answers, suggesting that our fundamental model of the cosmos might be missing a crucial piece. The first of these methods, the early universe approach, is like finding a detailed baby picture of the cosmos and using our knowledge of genetics to predict how the adult should look. This baby picture is the cosmic microwave background, or CMB, which is the oldest light in the universe. It's a fossilized glow from a time when the universe was just 380,000 years old, a hot, dense soup of particles and radiation that finally cooled enough for light to travel freely. We have mapped this afterglow with breathtaking precision using satellites like Planck, and it shows a universe that is almost, but not perfectly, uniform. These tiny fluctuations in temperature, tiny ripples in the fabric of the infant cosmos, are the seeds that would eventually grow into all the galaxies and clusters we see today. By applying our extremely well-tested understanding of physics and gravity, embodied in our standard model of cosmology, we can run a cosmic simulation forward in time. We can input the initial conditions from the CMB and calculate exactly how this universe should evolve, predicting what the Hubble constant should be today. This powerful method, which relies on the physics of the very young universe, gives us a value of around 67 kilometers per second per megaparsec. On the other side of the timeline, we have the late universe method, which is essentially an ultra-modern, high-precision version of Edwin Hubble's original technique. Instead of looking back at the universe's infancy, we are measuring its current state. This involves building a meticulous cosmic distance ladder, using parallax to calibrate Cepheid variable stars, then using those Cepheids to calibrate the peak brightness of Type 1, a supernova in nearby galaxies. This entire chain of measurement is then used to gauge distances to faraway galaxies, whose redshifts we can also measure. It's a direct, empirical measurement of the expansion rate in our cosmic neighborhood. This method, refined over decades with data from the Hubble Space Telescope and other world-class observatories, consistently returns a higher, faster value, around 73 kilometers per second per megaparsec. The local universe appears to be expanding roughly 9% faster than the baby picture from the CMB says it should be. The staggering part is that both methods have been refined to such a degree that their error margins are now incredibly small, meaning the gap between them is highly significant. It's not that one is sloppy, it's that they are fundamentally disagreeing. This Hubble tension is now one of the most exciting and urgent puzzles in all of science, because it strongly hints that our standard model of cosmology, while incredibly successful, is incomplete. We may need new physics to reconcile these two conflicting stories. Perhaps dark energy, which we have been assuming is a constant force embodied by Einstein's cosmological constant, isn't constant at all. Maybe it has been evolving over time, growing stronger and pushing the expansion to speed up more recently than our models predict. Another compelling possibility is the existence of a new, previously unknown type of neutrino or other exotic particle that flooded the early universe, subtly changing how it evolved and throwing off the predictions from the CMB. Or, most radically of all, this tension could be a sign that our understanding of gravity itself, described by Einstein's theory of general relativity, needs to be modified on the largest cosmic scales. Whatever the solution turns out to be, this isn't a failure of science. It's science at its best. A clear, unambiguous anomaly has emerged, pointing the way toward a deeper and more complete understanding of the fundamental forces that have shaped our universe from its first moments to the present day. To peer back into the universe's infancy and measure its expansion from the very beginning, we need a time machine, and in many ways, that's exactly what the Planck satellite was. Operated by the European Space Agency from 2009 to 2013, Planck was not looking at galaxies or stars. It was designed to capture the oldest photograph ever taken, an image of the universe when it was just a newborn, a mere 380,000 years old. The light it collected is known as the cosmic microwave background, or CMB, and it is the relic heat from the Big Bang itself. After the initial hot, dense explosion, the universe was an opaque fog of plasma, so thick that light particles, photons, couldn't travel freely. They were constantly bouncing off free electrons. But as the cosmos expanded and cooled, it eventually reached a temperature where electrons could combine with protons to form the first neutral atoms. In that moment, known as recombination, the fog suddenly cleared. The photons, once trapped, were finally set free to travel across the universe, and we see that first burst of liberated light today as a nearly uniform glow filling all of space. The Planck satellite's mission was to map this glow with an accuracy that was almost unimaginable just a generation ago. The image it produced, often described as a mottled, blue and gold oval, is arguably one of the most important in all of science. It doesn't look like much at first glance, just a speckled background, But those specks are everything. They represent tiny variations in temperature, minute fluctuations of just millionths of a degree above or below the average. These are not random imperfections. They are the cosmic seeds of all structure. These infinitesimal ripples in density are the gravitational blueprints for everything that would eventually form every galaxy cluster, every spiral galaxy, every star, and every planet owes its existence to the patterns imprinted in this ancient light. They are the result of quantum fluctuations from the universe's first instance, stretched to cosmic proportions by a period of hyper-expansion called inflation. So, how do these tiny temperature differences in an ancient glow allow us to calculate the universe's expansion rate today? It all comes down to using this baby picture as the ultimate initial condition for a cosmic simulation. Cosmologists have an incredibly robust model for how gravity and matter interact, governed by Einstein's theory of general relativity. By carefully analyzing the precise statistical patterns of these hot and cold spots in the Planck map, their sizes, their distribution, their correlation scientists can deduce the fundamental ingredients of the cosmos at that very early time. They can determine the total density of the universe, the amount of ordinary matter, the amount of dark matter, and the geometry of space itself. Think of it like a master baker who, by looking at a precise recipe and knowing exactly how ingredients interact, can predict the exact size and texture of the finished loaf of bread. The SAMB gives us the original recipe. With these initial conditions locked in, we run the clock forward. Our understanding of physics allows us to model how those tiny density ripples would grow over billions of years, pulled by gravity into the vast cosmic web of galaxies and clusters we observe today. The rate at which this structure forms is exquisitely sensitive to the expansion history of the universe. A universe that expands too quickly would stifle the growth of galaxies. A universe that expands too slowly would allow for more clumping. The Planck data, when plugged into our standard model of cosmology, provides a stunningly precise prediction for what the Hubble constant should be in the present day. This prediction, derived entirely from the physics of the infant universe, lands squarely at about 67 kilometers per second per megaparsec. This value is not a direct measurement of current expansion, but rather a profound prediction based on our deepest theories of cosmic evolution. The staggering success of this model in accurately predicting so many other observable features of the universe gives cosmologists great confidence in its result, which is why the persistent conflict with the direct measurements from the local universe has created such a fascinating and urgent mystery. So, while the Planck satellite gives us a pristine view of the universe's baby picture, another team of astronomers has been focused on taking a detailed snapshot of the cosmos in its adulthood. This ambitious effort is known as the SH0ES project, which stands for supernova, and H0 for the equation of state of dark energy. Led by Nobel laureate Adam Rees, the SH0ES team has dedicated over a decade to making the most precise direct measurement of the Hubble constant possible, using our local, modern universe as their laboratory. Their approach is a monumental exercise in cosmic metrology, meticulously building and calibrating the cosmic distance ladder rung by rung to eliminate any possible sources of error. Their goal is straightforward but incredibly challenging: to measure the current expansion rate with such overwhelming precision that the uncertainty around it virtually disappears. Yet, the more precise their measurements have become, the more they have cemented a profound disagreement with the early universe predictions from Planck. The core of the SH0ES method is to create a direct, unbroken chain of measurements from our solar system all the way out to distant supernova. The most critical and difficult link in this chain has always been the connection between Cepheid variable stars and Type 1, a supernova. To understand why, consider this: we use Cepheids to measure the distance to galaxies, and we use Type 1, a supernova, as even brighter standard candles to reach much further. But to trust the supernova, we first have to calibrate their true brightness. We do this by finding galaxies that are close enough to contain both Cepheids and have hosted a recorded Type 1, a supernova, in the past. By using the Cepheids to get an extremely precise distance to that galaxy, we can then look at the observed peak brightness of the supernova that occurred there and work backwards to determine its true intrinsic power. It's like having a light bulb factory in a building. If you know the exact distance to the building, you can measure the apparent brightness of a bulb that flashes inside and calculate its true wattage with perfect confidence. This is where the Hubble Space Telescope became an indispensable tool. Its crystal-clear vision, unobstructed by Earth's atmosphere, allowed the SH0ES team to peer into dozens of galaxies and pick out individual Cepheid variables even in crowded galactic cores, something that is incredibly difficult to do from the ground. The team embarked on a vast observing campaign, painstakingly observing the pulsations of thousands of Cepheids in these crucial calibration galaxies. They then used this robust Cepheid supernova calibration to measure distances to faraway galaxies that are receding from us at high speeds due to the cosmic expansion. The final result of this Herculean effort is a Hubble constant value of about 73.04 kilometers per second per megaparsec, with an astonishing uncertainty of just over 1%. This number represents the expansion rate as measured today in our cosmic neighborhood, and this is where the plot thickens into a full-blown mystery. The SH0ES team's value of 73 is in clear, significant tension with the Planck collaboration's value of 67. This isn't a case of one being right and the other wrong. Both teams have scrutinized their methods for years, searching for any hidden systematic errors that could explain the discrepancy. The SH0ES team has cross-checked their Cepheid measurements with other distance indicators, like the tip of the red giant branch method, and the tension not only remains, but has grown stronger as the data has improved. The difference is now at a level of about 5 sigma in statistical terms, which essentially means the probability that this is just a random fluke is less than 1 in a million. The universe, through these two exquisitely precise experiments, appears to be telling us two different stories about its current rate of expansion. This persistent disagreement isn't just a minor detail. It is a glaring clue that our standard model of cosmology, for all its successes, might be missing a crucial piece of the puzzle, a piece that could lead us to a deeper understanding of dark energy, gravity, or the very nature of the cosmos itself. This persistent disagreement between our cosmic baby picture and our local measurements isn't just an annoyance for astronomers. It's a beacon, a tantalizing clue that we might be on the verge of a monumental breakthrough. What if the Hubble tension isn't a sign that we've made a mistake, but rather a signal that our universe is governed by rules we haven't yet discovered? This is the thrilling frontier of cosmology today, where the discrepancy in the Hubble constant is driving physicists to propose radical new ideas that could fundamentally reshape our understanding of reality. The most promising of these ideas involve adding new, exotic ingredients to our cosmic recipe, or radically rethinking the ones we already have. One compelling line of thought points to the very first moments after the Big Bang. Our standard model calculates the evolution from the cosmic microwave background based on a specific amount of radiation present in the early universe, largely from known particles like photons and neutrinos. But what if there was an extra component, something we haven't detected? Cosmologists call this hypothetical component dark radiation. This wouldn't be radiation in the sense of light, but rather a form of energy made up of fast-moving, lightweight particles that barely interact with normal matter. Think of them as ghostly cousins to the neutrinos we know, but even more elusive, How would this solve the tension? The presence of this additional dark radiation in the early universe would have altered how quickly the initial cosmic soup could clump together to form the first structures. This, in turn, would change the precise pattern of the hot and cold spots in the CMB that the Planck satellite measured. To make the observed CMB data fit, our models would then have to adjust the Hubble constant to a higher value, potentially bridging the gap with the SH0ES team's local measurement. It's as if we discovered an unknown ingredient was in the cosmic batter all along, one that changes how we predict the final cake should rise. Another, perhaps even more dramatic, possibility is that we have misunderstood the dominant force in the cosmos, dark energy. In our standard model, we treat dark energy as a constant, an unchanging force represented by Einstein's cosmological constant. This constant energy density, inherent to space itself, leads to the accelerated expansion we observe. But what if dark energy isn't constant? What if its strength has been changing over the history of the universe? This concept is known as dynamical dark energy or quintessence. In this scenario, dark energy could have been weaker in the distant past, allowing the universe to evolve in a way that matches the Planck CMB data, which points to a lower expansion rate. Then, more recently in cosmic terms, this dark energy could have grown stronger, giving the expansion an extra push that we now measure locally as a faster rate. This would mean the acceleration of the universe isn't a steady, relentless push, but a variable force that has turned up over time. If true, this would completely transform our vision of the cosmos's ultimate fate, suggesting a future that could be far more violent and expansive than we currently envision. Beyond these additions to our cosmic inventory, some physicists are considering an even more foundational revision. Perhaps Einstein's theory of general relativity, our magnificent description of gravity for over a century, needs modification on the largest conceivable scales. General relativity has passed every test with flying colors within our solar system and in our studies of binary pulsars, but its behavior across the entire observable universe is a different matter entirely. Could gravity behave slightly differently over these vast, cosmic distances? Theories of modified gravity propose that the force's strength might diminish or change in form across billions of light years. A weaker gravity on cosmic scales would mean less pull to slow down the expansion, which could naturally lead to a higher present-day expansion rate without conflicting with the early universe data. While these theories are complex and challenging to test, the Hubble tension provides a crucial observational anchor point, a real-world puzzle that these new models must solve to be taken seriously. The incredible thing about this entire situation is that it represents science at its most dynamic and self-correcting. We are not facing a dead end, but a fork in the road with multiple, exciting paths forward. New telescopes and missions are being designed with the explicit goal of cracking this mystery. The Nancy Grace Roman Space Telescope, set to launch later this decade, will survey thousands of distant supernovae and millions of galaxies, providing a new, overwhelming torrent of data to measure the expansion history with unprecedented precision. Meanwhile, next-generation observatories will map the cosmic microwave background with even finer detail, searching for any subtle fingerprints that these new physics might have left in the universe's first light. The Hubble tension is more than a disagreement between two numbers. It is a conversation the universe is having with us, a hint that there is a deeper layer of reality waiting to be uncovered. Whether the answer lies in ghostly radiation, an evolving dark energy, or a modification to gravity itself, the resolution to this cosmic controversy promises to rewrite our textbooks and reveal a universe far stranger and more wonderful than we ever imagined. But how do we actually see this expansion happening across the vast emptiness of space? The answer lies in a subtle, yet profound, property of light itself, a phenomenon known as redshift. Think about the last time you heard an ambulance or a police car race past you with its siren wailing. As the vehicle approaches, the sound waves are compressed, pushing them closer together, which makes the siren's pitch sound high and sharp. The moment it passes you and begins moving away, those same sound waves get stretched out, making the pitch drop to a lower, deeper tone. This is the Doppler effect in action for sound, and light behaves in an almost identical way. When a source of light is moving away from us at tremendous speed, the waves of light itself get stretched out. Since red light has the longest wavelengths in the visible spectrum, this stretching causes the light to shift toward the red end, hence the term redshift. For astronomers, this cosmic redshift is the primary evidence that galaxies are rushing away from us, but there's a crucial distinction to make. The redshift we observe from distant galaxies isn't primarily because the galaxies are rocketing through space, like that ambulance driving down a street. The dominant cause is that the very fabric of space between us and the galaxy is expanding. As a beam of light travels for billions of years across this expanding cosmos, the space it's traveling through stretches, and the light wave gets stretched along with it. The longer the journey, the more stretching occurs, and the greater the redshift we measure. It's as if the ambulance wasn't just driving away, but the road itself was a stretching rubber band, elongating the sound waves far more than the vehicle's own engine ever could. This cosmological redshift is a direct imprint of the universe's expansion on the light that travels through it. So, how do we measure this subtle color shift with any accuracy? Astronomers use an incredible instrument called a spectrograph, attached to a powerful telescope. A spectrograph doesn't just capture a pretty picture of a galaxy. It acts like a cosmic prism, splitting the galaxy's gathered light into a full rainbow spectrum. But this isn't a smooth, perfect rainbow. Within it are dark lines, specific gaps where elements in the galaxy's outer atmosphere, like hydrogen, helium, and calcium, have absorbed very specific wavelengths of light. Every element has its own unique fingerprint, a predictable pattern of these absorption lines. We know the exact rest wavelength of these lines from laboratory experiments here on Earth. When we analyze the spectrum of a distant galaxy, we find that this entire fingerprint pattern has been shifted. All the lines are still in the same order, but they've all moved en masse toward the redder, longer wavelength end of the spectrum. By measuring exactly how far these familiar cosmic barcodes have shifted from their known positions, we can calculate the galaxy's recessional velocity with astonishing precision. The formula is beautifully straightforward. The greater the redshift, the faster the galaxy is speeding away from us. This simple measurement, repeated for thousands upon thousands of galaxies, was what allowed Edwin Hubble to discover his famous law. He saw that the redshift was always proportional to distance. The farther the galaxy, the greater its redshift, and thus the faster its retreat. This single, elegant observation transformed our understanding of the cosmos from a static collection of stars into a dynamic, expanding entity, providing the first direct evidence for the Big Bang and setting the stage for the even more shocking discovery of our accelerating universe. Redshift is the universe's own speedometer, written in the very light that reaches our telescopes, and so we arrive at the central mystery, the invisible elephant in the cosmic room that is responsible for the universe's runaway expansion, dark energy. We've mapped its effects with stunning precision. We know it's there, we know it's dominant, and we know it's pushing galaxies apart at an ever-increasing rate. Yet, we have almost no idea what it actually is. To put its staggering dominance into perspective, if you were to take the entire energy content of the cosmos and divide it into a pie chart, dark energy would claim a whopping 68% of the whole pie. All the galaxies, stars, planets, nebulae, and every single particle of ordinary matter that we can see and touch accounts for less than 5%. The remaining 27% is the gravitational glue of dark matter, another profound mystery, but one that still plays by the familiar rules of gravity, pulling things together. Dark energy, by contrast, is playing a completely different game, one that involves a relentless and repulsive push. The leading and simplest explanation for this bizarre force is a concept that dates back to Albert Einstein himself, though for very different reasons. He called it the cosmological constant. In 1917, when Einstein was applying his new theory of general relativity to the universe as a whole, he, like most scientists of his time, believed the cosmos was static and eternal. But his equations kept telling him that such a universe would be unstable. It would either collapse under its own gravity or expand. To force his equations to describe the static universe he thought was real, he invented a fudge factor, a term represented by the Greek letter lambda, which represented a constant, repulsive energy inherent to the fabric of empty space itself. This energy would perfectly balance the inward pull of gravity, creating a stable, unchanging cosmos. Years later, when Edwin Hubble discovered the universe was indeed expanding, Einstein famously discarded his cosmological constant as his greatest blunder. Yet, in a stunning twist of fate, modern cosmology has resurrected it. The acceleration discovered in 1998 suggests that the universe does indeed contain a constant energy density, filling the vacuum of space, behaving almost exactly like Einstein's once rejected idea. But what does this actually mean? Imagine the vacuum of space. We think of it as truly empty, a perfect nothingness, but quantum physics tells us that even in the deepest void, there is a seething, bubbling froth of activity. Virtual particles and antiparticles constantly pop into and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This gives the vacuum itself a baseline energy, a vacuum energy. The cosmological constant idea proposes that this vacuum energy is exactly that, a constant. In every single cubic centimeter of space, whether in the emptiness between galaxies or right here in this room, there is a tiny, fixed amount of this repulsive energy. And because space itself is expanding, creating more cubic centimeters of vacuum, the total amount of this repulsive energy grows, driving the expansion faster and faster over time. It's a truly mind-bending concept. The ultimate source of the cosmic acceleration is not some distant engine, but a fundamental property of space itself, everywhere at once. This leads to the most counterintuitive consequence of dark energy, its gravitational behavior. According to Einstein's theory, gravity isn't just about mass, it's about energy and pressure. We're used to matter, which has positive energy density and negligible pressure, creating the familiar, attractive gravity that holds us on Earth and keeps planets in orbit. But dark energy, as described by the cosmological constant, has a tremendously powerful negative pressure. Think of it like a stretched rubber band. It has a tension, a negative pressure, that wants to pull it back together. Dark energy is the opposite. It's a negative pressure that wants to push outwards. In the equations of general relativity, this intense negative pressure acts as a source for gravitational repulsion. So, while matter and dark matter create an attractive gravitational field that pulls the cosmos together, dark energy creates a repulsive gravitational field that pushes it apart. This is the cosmic tug-of-war that defines our universe's fate. For the first 9 billion years or so, the density of matter was so high that its attractive gravity dominated, slowing the expansion down. But as the universe expanded and matter thinned out, the constant energy density of dark energy eventually became the dominant force, its repulsive gravity taking over and kicking off the era of acceleration we now observe. The fact that we live at the precise cosmic moment when this transition occurred is a remarkable coincidence, one that allows us to witness and study this fundamental shift in the universe's dynamics. The story of dark energy is deeply intertwined with one of the most famous about-faces in the history of science, a tale that centers on none other than Albert Einstein and what he later called his greatest blunder. It begins in 1917, just 2 years after he had completed his monumental theory of general relativity. This new theory described gravity not as a force, but as a curvature of space and time itself, warped by the presence of mass and energy. When Einstein began applying these profound equations to the universe as a whole, he ran into a problem that seemed to defy his own work. According to the calculations, the universe he was describing was fundamentally unstable. The collective gravitational pull of all the matter in the cosmos should be causing it to either collapse inward upon itself or to expand outward. Yet, the prevailing scientific wisdom of the day, supported by the observational evidence available at the time, insisted that the universe was static, eternal, and unchanging. The Milky Way was the entirety of the known cosmos, and it appeared to be in a steady, unmoving state. To resolve this glaring contradiction between his beautiful theory and the accepted reality, Einstein made a decision that would haunt him for the rest of his life. He modified his equations. He introduced a new term, a fudge factor represented by the Greek letter lambda, which he called the cosmological constant. This term represented a repulsive force, an anti-gravity that was inherent to the very fabric of empty space itself. Its purpose was purely mathematical, to precisely counteract the inward pull of gravity on cosmic scales, creating a delicate balance that would allow for a static, unchanging universe. It was a brilliant mathematical fix, but one that lacked any physical motivation beyond making the theory fit the prevailing belief. For Einstein, the universe simply had to be static, and the cosmological constant was the tool he used to make it so. The irony, of course, is that the universe was not static at all. Just over a decade later, in 1929, Edwin Hubble, working with the powerful Hooker telescope at Mount Wilson, presented the incontrovertible evidence. By measuring the redshifts of distant galaxies and using Cepheid variable stars to gauge their distances, Hubble demonstrated that the universe was not standing still, but was in fact expanding, with galaxies racing away from each other. The cosmos was dynamic, not static. Upon learning of this discovery, Einstein immediately realized his mistake. He had allowed his preconceived notions about the universe to override the pure prediction of his own theory, which had actually foreseen an expanding cosmos. He famously traveled to Mount Wilson, looked through the telescope, and later declared the introduction of the cosmological constant to be the biggest blunder of his entire career. He discarded lambda from his equations, and for decades, it was treated as an embarrassing footnote, a moment when even the greatest scientific mind had faltered. The final, breathtaking twist in this story came nearly 70 years later with the discovery of the accelerating universe in 1998. Those observations of distant supernovae revealed that not only was the universe expanding, but the expansion was speeding up. Something was actively pushing galaxies apart, a mysterious, repulsive force. And when cosmologists raced to their equations to explain this baffling phenomenon, they found the answer waiting for them in the historical dustbin. The simplest, most elegant way to describe this repulsive force was to resurrect Einstein's long-abandoned cosmological constant. The lambda term was back, but with a completely new and profound meaning. Einstein had been right to include it, but for entirely the wrong reason. He had introduced it to hold the universe static, but its true purpose was to describe the dark energy that drives the cosmic acceleration. It's a stunning historical full circle, a concept that was born from a perceived error, discarded as a mistake, and then triumphantly reclaimed as the key to understanding the dominant force in our universe. It stands as a powerful lesson in science. Sometimes, the math knows things we don't, and even our greatest blunders can contain a seed of profound, unforeseen truth. But if the force driving this acceleration is the great cosmic mystery, then the stuff it's pushing around adds another layer of profound bewilderment. When we add up everything that makes up our universe, every particle, every wave, every form of energy, the final accounting is both humbling and startling. Think of the cosmos as a vast, cosmic pie. If we were to slice it up according to its fundamental ingredients, the portions we would serve are almost unbelievable. This is our universe's energy budget, and the recipe is nothing like what we might have guessed. The single largest slice, a staggering 68% of the entire pie, is the very mystery we've been discussing: dark energy. This is the repulsive force embedded in the vacuum of space itself, driving the acceleration. The next slice, accounting for about 27% of the cosmos, is another enigma: dark matter. This is a substance that reveals itself only through its immense gravitational pull. We can see its effects in the way galaxies spin far too quickly to be held together by the gravity of their visible stars alone, and in the way massive galaxy clusters bend the light from objects behind them, a phenomenon known as gravitational lensing. Dark matter is fundamentally different from dark energy. It doesn't push, it pulls. It acts as the cosmic scaffolding, an invisible skeleton that provided the gravitational wells for ordinary matter to collapse into, forming the galaxies and the vast cosmic web we observe today. Yet, despite making up over a quarter of the universe, it does not emit, absorb, or reflect any light. It is completely transparent and interacts with normal matter only through gravity, making it utterly invisible to our telescopes. This brings us to the final, tiny sliver of the cosmic pie, a mere 5%. This is everything else. This 5% encompasses every single thing we have ever seen, touched, or measured directly. It includes every star burning in the night sky, every planet orbiting those stars, every nebula glowing with brilliant colors, every black hole, every asteroid, and every single living creature. It is you, me, the air we breathe, and the ground beneath our feet, all the richness and complexity of our experienced reality, all the chemistry, biology, and physics that we have spent centuries unraveling accounts for just 1/20th of the total content of the universe. This portion is what scientists call normal or baryonic matter, and its shocking scarcity is one of the most profound realizations of modern cosmology. We are not made of the dominant stuff of the cosmos. We are a rare and exotic afterthought, a delicate froth on the surface of a deep, dark ocean whose true composition remains almost entirely unknown to us. This cosmic recipe forces a perspective shift that is both awe-inspiring and deeply unsettling. For all our technological achievements and scientific understanding, we have only just begun to catalog 5% of what actually exists. 95% of the universe is made of components that are, for now, completely mysterious. We have given them names dark energy and dark matter, but these names are essentially placeholders for our ignorance. They are labels for gravitational effects we cannot explain with the known laws and particles. This means our current model of physics, for all its power and precision, is fundamentally incomplete. It can beautifully describe the behavior of the 5%, but it falls silent when faced with the 95% that governs the overall fate of the cosmos. Every time we look up at the night sky, we are seeing only the barest hint of what is truly out there, a glimmering 5% tip of a cosmic iceberg whose dark, massive bulk lies hidden beneath the surface of our perception. This relentless acceleration driven by dark energy doesn't just alter our present-day map of the cosmos. It scripts a final chapter for the universe that is both majestic and profoundly desolate. The most likely ultimate fate, based on the expansion rate we measure today, is a scenario cosmologists call the Big Freeze or heat death. Imagine rewinding the cosmic film we've been watching and then letting it play out trillions, then quadrillions of years into the future. The first act of this final story sees the acceleration we observe today continuing to intensify. The space between galaxy clusters stretches so rapidly that the cosmic horizon closes in. Galaxies that are not already bound together by gravity will find their connections severed. The light from those distant islands of stars will one day simply be unable to cross the ever-widening gulf. Their photons, desperately racing toward us, will find the space between expanding faster than they can travel. The observable universe will effectively shrink, not in size, but in content, as one galaxy after another winks out of view, disappearing over a horizon from which no information can ever return. Our own local group of galaxies, bound together by gravity, will remain, eventually merging into one massive, aging galaxy, a single, isolated city in an otherwise dark and empty metropolis. Within this lone, surviving galaxy, the second act unfolds over eons far longer than the current age of the universe. The era of star formation will draw to a close. The great clouds of gas and dust, the raw material for new suns, will either be used up in one final burst of stellar birth or be flung out of galaxies entirely by the violent deaths of the last massive stars. One by one, the furnaces will shut down. The most massive, brilliant blue stars are the first to go, exploding as supernovae after just a few million years. Middleweight stars like our own sun will last longer, but eventually they too will exhaust their hydrogen fuel, puff off their outer layers, and cool into dense white dwarf embers. The smallest, red dwarf stars are the most frugal, burning their hydrogen so slowly that they could shine for trillions of years, but even their immense longevity has a limit. In a future so distant it defies human comprehension, the last red dwarf will finally flicker and die. The galaxy, once a vibrant pinwheel of light and color, will become a cosmic graveyard, populated only by the corpses of stars, black holes, neutron stars, and cold, dark white dwarfs, all drifting in an ever-deepening and permanent night. The final act of the Big Freeze is the most extreme, governed by the slow, inexorable laws of particle physics operating over timescales that are literally unimaginable. In this cold, dark universe, even the stellar corpses won't last forever. A process predicted by Stephen Hawking, known as Hawking radiation, suggests that black holes are not entirely black. Due to quantum effects at their event horizons, they are theorized to slowly leak energy and lose mass. For a stellar mass black hole, this evaporation process would take around 10 to the 67 years, a 1 followed by 67 zeros. For the supermassive black holes at the centers of galaxies, the process would take well over 10 to the 100 years, but eventually, even these most formidable gravitational anchors will vanish in a final, faint pop of radiation. What remains is a universe that is almost perfectly empty. The occasional, ultra-rare proton or neutron might decay, if such a process is possible, leaving behind only the lightest particles like electrons, positrons, and neutrinos, all scattered so infinitely far apart by the expansion that they will never interact again. The temperature of the entire universe will asymptotically approach absolute zero, the point where all molecular motion ceases. There will be no more sources of energy, no more temperature differences to exploit, no more work that can be done. It will be a state of maximum entropy, a uniform, silent, and utterly static sea of nothingness. This is the direct and chilling consequence of the accelerating expansion we measure today, a future dictated not by fire, but by ice, where the universe achieves a final, permanent, and perfectly lifeless equilibrium. While the Big Freeze represents a slow, cold, and gradual descent into darkness, there exists a far more violent and dramatic alternative for the cosmos, a scenario born from the unsettling possibility that dark energy might not be constant after all. This is the fate known as the Big Rip, and if it were to come to pass, the universe's final moments would be a spectacularly destructive crescendo. The key to this terrifying possibility lies in the nature of dark energy's repulsive force. In our standard model, with Einstein's cosmological constant, this force remains steady over time. But what if, instead of being constant, dark energy actually grows stronger? What if its repulsive power intensifies as the universe expands? This form of dark energy is sometimes referred to as phantom energy, and its implications are nothing short of apocalyptic. In this scenario, the acceleration we observe today wouldn't just continue, it would exponentially increase, becoming infinitely powerful in a finite amount of time. The mechanics of the Big Rip are as methodical as they are horrifying. It would be a process of cosmic disintegration, starting on the largest scales and working its way down to the very fabric of reality itself. The first structures to fall would be the largest gravitationally bound systems. As dark energy's repulsive force grows, it would eventually exceed the gravitational glue holding galaxy clusters together. These vast cities of galaxies, which have been sailing away from each other for billions of years, would be the first to be torn asunder from within. Next, the force would target individual galaxies, the Milky Way, Andromeda, and all their neighboring dwarfs, which are currently on a collision course driven by their mutual gravity, would find that bond shattered. The phantom energy would overwhelm the gravity that holds a galaxy's spiral arms together, sending stars flying off into the ever-expanding void like sparks from a pinwheel. But the destruction would not stop there. The relentless strengthening of dark energy would then set its sights on individual solar systems. The gravitational tether that keeps planets in stable orbits around their parent stars would be the next to snap. A star and its planets would be violently ripped apart from one another. Then, the force would turn inward. It would attack the stars and planets themselves. A star is a delicate balance between the inward crush of its own gravity and the outward push of nuclear fusion in its core. The Big Rip's phantom energy would disrupt this equilibrium, tearing the star apart. Planets would be shredded, their material scattered into the void. Finally, in the last fleeting moments before the end, the force would target the building blocks of matter itself. The very molecules, atoms, and subatomic particles that constitute everything we know would be ripped asunder. The nuclear forces that bind protons and neutrons together in an atomic nucleus, forces that are trillions of times stronger than gravity, would be overcome. In the final fraction of a second, space-time itself would be torn to pieces. The universe would not end with a whimper, but with a literal and fundamental rending of reality at every possible scale. The critical question, of course, is whether this terrifying scenario is supported by our current observations. To answer that, cosmologists use a parameter called the equation of state of dark energy, denoted by the letter W. This number describes the relationship between the pressure and density of dark energy. In the simple cosmological constant model, this value is exactly -1. If W is exactly -1, we live in a universe headed for a big freeze. However, if W is less than -1, for example, -1.1 or -1.2, then dark energy has the phantom quality that leads to a big rip. The timing of the rip depends on how much less than -1 the value is. The more negative, the sooner the universe would meet its end. Current data from the cosmic microwave background, supernova, and large-scale galaxy surveys all tightly constrain this value. The latest measurements place W at very close to -1, with only the tiniest margin for error. At the moment, the data strongly favors the constant dark energy of the cosmological constant and the long, cold future of the Big Freeze. However, the door to the Big Rip is not completely closed. The uncertainties in our measurements, while small, mean we cannot yet rule out a value for W that is ever so slightly less than -1. It remains a haunting, albeit unlikely, possibility on the farthest fringes of our cosmic predictions. This underscores the immense importance of ongoing and future missions, like the Nancy Grace Roman Space Telescope and the Euclid satellite, which are designed to measure the properties of dark energy and the expansion history of the universe with unprecedented precision. They will measure W with such fine detail that we will know, with near certainty, whether our universe is destined for a slow, frozen eternity or a far more explosive and immediate demise. The Big Rip stands as a powerful reminder of just how high the stakes are in our quest to understand dark energy, a force that holds not just the history of the cosmos in its grip, but its ultimate, final moment. While dark energy is the force pushing the cosmos apart on the grandest scales, there is another, equally mysterious component working in direct opposition, sculpting the universe into the intricate structure we observe. This is dark matter, and its role is fundamentally different. Think of it as the universe's invisible architect and construction crew, all rolled into one. Dark energy provides the repulsive force that stretches the canvas of space, but dark matter provides the gravitational wells that gather ordinary matter into the magnificent structures painted upon that canvas: the galaxies, the clusters, and the vast cosmic web that connects them all. Without dark matter's relentless pull, the accelerating expansion would have long since diluted the universe into a thin, featureless haze, and we would not be here to witness any of it. The most compelling evidence for this invisible scaffolding comes from observing how galaxies behave. When astronomers measure the rotation speeds of stars and gas clouds within spiral galaxies, they find something deeply puzzling. According to the laws of gravity, stars on the outer edges of a galaxy, far from the bright, central bulge of stars, should be orbiting much more slowly, just as Pluto orbits the Sun far more sluggishly than Mercury. But the data reveals the opposite. These distant stars and gas clouds are whipping around at almost the same high speed as those closer in. The only feasible explanation is that each galaxy is embedded within an enormous, diffuse sphere of invisible matter, a dark matter halo, whose gravity is providing the extra pull to keep those outer stars from flying off into intergalactic space. This halo extends far beyond the visible edge of the galaxy, and its total mass is typically 5 to 10 times greater than all the stars and gas we can see. Dark matter is the gravitational glue that holds galaxies together, a silent, unseen anchor in the accelerating cosmic flow. This gravitational influence scales up dramatically to the very largest structures in the universe. When we map the cosmos on the scale of billions of light years, we don't see a random sprinkling of galaxies. Instead, we find a cosmic web, a magnificent architecture of dense galaxy clusters, connected by long, delicate filaments of galaxies and separated by enormous, near-empty voids. This web is the direct result of dark matter's gravitational pull, acting over billions of years. In the early universe, slight overdensities in the dark matter distribution, seeded by quantum fluctuations from the Big Bang, began to attract more and more dark matter through gravity. These regions became the gravitational skeletons for future structure. Ordinary matter, the 5% of the universe that we are made of, was then pulled along for the ride. As dark matter collapsed into vast, interconnected sheets and filaments, the ordinary matter followed, cooling and condensing to form the galaxies that now trace out the web's luminous pattern. The great voids are there because dark matter's gravity has pulled everything away from those regions, leaving behind cosmic deserts. This creates a fascinating and constant tug of war that defines the large-scale evolution of our universe. On one side, you have the relentless outward push of dark energy, which works to smooth everything out and drive structures apart. On the other, you have the persistent inward pull of dark matter's gravity, which works to clump matter together into ever denser knots. For the first 9 billion years of cosmic history, dark matter's gravity was the dominant force. It won the battle, allowing galaxies to form, clusters to assemble, and the great cosmic web to emerge. But as the universe expanded, the density of matter dropped, while the repulsive effect of dark energy remained constant or even grew stronger. Around 5 billion years ago, the balance of power shifted. Dark energy began to dominate, and the expansion of the universe started to accelerate. This doesn't mean the cosmic web is being torn apart. The gravitational bonds within individual galaxy clusters and groups are far too strong for that. Instead, it means that the vast, empty voids between the web's filaments are now stretching at an ever-increasing rate. The web itself is becoming more starkly defined, with galaxies flowing along the dark matter highways into the dense clusters, while the empty voids grow ever larger and more desolate. Dark matter built the cosmic cities, and dark energy is now accelerating the expansion of the barren lands between them, isolating each metropolitan cluster in its own island of gravity within an ever-widening sea of nothingness. But of course, the cosmic distance ladder and the afterglow of the Big Bang are not the only tools we have for charting the expansion of the universe. There is another, incredibly powerful method that uses the cosmos itself as a grand ruler, and it relies on a fossilized echo from a time when the universe was anything but silent. These are Barrian acoustic oscillations, or BAO for short, and they are essentially the ghostly imprint of sound waves that raced through the newborn cosmos, frozen in place and scaled up to a truly astronomical size. To understand how this works, we need to travel back to the universe's first few 100,000 years, to that hot, dense plasma we encountered with the cosmic microwave background. This primordial soup was a seething ocean of particles, primarily photons of light, protons, and electrons, all constantly interacting. Gravity was trying to pull the matter together into dense clumps, but the intense pressure of the radiation was pushing it all back out. This push and pull created a series of powerful pressure waves, essentially sound waves, that rippled outward through the plasma at a significant fraction of the speed of light. Imagine tossing a pebble into a still pond and watching the circular ripples spread outwards. Now, imagine that the pond suddenly and instantly froze solid, preserving those ripples exactly as they were in that single moment. This is precisely what happened in the early universe, at the moment of recombination, when the universe cooled enough for atoms to form and the fog cleared. The photons suddenly stopped pushing against the matter. The pressure waves lost their driving force and simply stopped in their tracks. They were instantly frozen into the fabric of the cosmos. The distance these sound waves managed to travel from their origin point before the universe became transparent is known as the sound horizon. This distance became a fixed, standard length etched into the distribution of matter. Today, that same scale is imprinted in two different ways, as the tiny temperature variations we see in the cosmic microwave background, and as a subtle preference for galaxies to be separated by a specific distance. This sound horizon is our cosmic standard ruler, and we know its true physical size with incredible precision from our understanding of the early universe's physics. So, how do we use this frozen ruler to measure expansion? The concept is beautifully straightforward. We know the actual physical length of this standard ruler from the early universe. Now, by looking out at the cosmos at different epochs, that is, at different distances, which also means looking back in time, we can measure the apparent size of this ruler as it appears to us. We do this by mapping the three-dimensional positions of millions upon millions of galaxies in huge sky surveys. When we analyze this cosmic cartography, we can statistically detect that galaxies are slightly more likely to be separated from each other by a specific scale, the size of that ancient sound wave, now stretched to nearly 500 million light-years due to the expansion of the universe. If we measure this preferred separation for a population of relatively nearby galaxies, we get one angular size for our standard ruler. When we then measure the same preferred separation for a population of extremely distant ancient galaxies, we find that the apparent size of the ruler is larger. This is not because the ruler itself grew. It's because the universe has expanded more dramatically along the line of sight to those more distant objects, stretching the apparent angular scale we observe. By comparing the known true size of the ruler to its apparent size at various cosmic distances, we can chart the expansion history of the universe with a method that is completely independent of the supernova distance ladder and the CMB. It provides a direct, geometric test of how space has stretched over billions of years, and its measurements powerfully and independently confirm the accelerating expansion we first saw in the light of dying stars. One of the most visually stunning and conceptually powerful tools for probing the expansion rate relies on nature's own magnifying glass, a phenomenon predicted by Einstein's theory of general relativity called gravitational lensing. Imagine space-time as a vast, flexible sheet. When you place a massive object on that sheet, like a galaxy or a galaxy cluster, it creates a deep depression, a gravitational well. Now, when a beam of light from a distant object travels through the cosmos and passes near this massive well, its path isn't straight. It follows the curvature, bending around the heavy object. From our perspective, this means the light from a single, distant source can be warped, magnified, and even split into multiple images, creating beautiful cosmic mirages like Einstein rings or crosses. This effect does more than just create pretty pictures. It provides a completely independent and geometric way to measure cosmic distances, offering a crucial check on the Hubble constant that bypasses the traditional distance ladder entirely. The most precise application of this for measuring expansion is a sophisticated technique known as time delay cosmography. This method often involves a specific cosmic setup, a brilliantly bright and distant quasar, the active, superheated core of a young galaxy, located directly behind a massive foreground galaxy cluster acting as the lens. The cluster's immense gravity bends the quasar's light, not just distorting it, but often splitting it into several distinct mirror images that we can see arrayed around the lensing cluster. Now, here's where it gets truly fascinating for cosmology. The paths that light takes to form each of these separate images are not the same length. Some paths loop around the gravitational well a little more, while others take a more direct, but still bent, route. Since light always travels at the same speed, these path length differences mean the light for each image arrives at Earth at a slightly different time. One image might show a flare from the quasar today, while another image of that exact same flare might show up days, weeks, or even months later. By patiently monitoring these multiple images over years, astronomers can measure this time delay with exquisite precision. They wait for a flicker in the quasar's brightness, a natural flare, and then clock how long it takes for that identical flicker to appear in the other lensed images. This measured time delay is the direct observable, but to convert this into a distance, and thus a measurement of the Hubble constant, requires building an incredibly detailed model of the lens itself. Astronomers use the distorted shapes of background galaxies, bent into long, faint arcs, to map the precise distribution of mass in the foreground cluster, including both its visible stars and, most importantly, its immense halo of dark matter. This model tells them how deep the gravitational well is and how much the light paths are bent. With this model in hand, the time delay measurement essentially gives them the absolute physical scale of the entire system. The combination of the time delay and the lens model yields a direct measurement of the distance to the lensing cluster and the background quasar. This is a profoundly different route to the Hubble constant. It relies purely on geometry and the speed of light, completely independent of Cepheid variables, supernovae, or the physics of the early universe. It's like being able to measure the distance to a faraway mountain by using a known baseline and trigonometry, rather than by guessing the wattage of a light bulb on its peak. The H0LICOW collaboration, which stands for H0 lenses in Cosmogral Wellspring, has been a leader in this field, focusing on precisely these kinds of time delay measurements. Their results have been tantalizing, often yielding a Hubble constant value that intriguingly sits in the middle of the contentious gap between the Planck and SH0 measurements. This suggests that systematic errors might indeed be lurking in the other methods, or perhaps that the true expansion rate genuinely lies somewhere between the two extremes. Time delay cosmography is incredibly challenging. It requires years of patient monitoring and complex computer modeling to account for every ripple in the mass distribution of the lens. But as a method that relies on the fundamental geometry of space-time itself, it provides one of our cleanest and most powerful probes into the heart of the Hubble tension, offering a unique perspective that could ultimately help resolve the greatest crisis in modern cosmology. When we talk about the monumental task of measuring the universe's expansion, one instrument stands out as the undisputed champion in the modern era, the Hubble Space Telescope. It's no exaggeration to say that this single observatory, orbiting high above the distorting effects of Earth's atmosphere, has been the central protagonist in the story of the Hubble constant for over 3 decades. Its contributions have moved the field from rough estimates to a state of high-precision crisis, transforming a scientific curiosity into one of the most profound puzzles in all of physics. Named for the very man who discovered the expansion, Hubble was uniquely designed to pick up where its namesake left off, armed with a crystal-clear view and technology Edwin Hubble could only have dreamed of. Its mission was to do what ground-based telescopes struggled with: see the cosmos with a clarity that would allow us to measure the fundamental markers of distance with unwavering confidence, reaching far deeper into the cosmos than ever before. 2 of its most ambitious projects, the Key project on the extragalactic distance scale and the subsequent SHOES program, were laser-focused on a single, monumental goal: to measure the Hubble constant with an error margin of just 10%, and then to push that uncertainty down to an astonishing 1%. This was not a side project. It was a core reason for Hubble's existence. The biggest hurdle in this quest had always been the first crucial step on the cosmic distance ladder: getting a precise, direct measurement of the distances to nearby galaxies that contain both Cepheid variables and Type 1, a supernova. From the ground, viewing a Cepheid in a distant galaxy is like trying to distinguish a single, specific firefly in a massive, glowing swarm from miles away through a thick, turbulent atmosphere. The twinkling that makes stars seem romantic to us is the enemy of precision astronomy, blurring and distorting the tiny, rhythmic changes in a Cepheid's light that we need to measure its pulse period. Hubble's vantage point in space eliminated this problem entirely. With its pristine vision, it could do something revolutionary: resolve individual Cepheid stars in the crowded cores of galaxies tens of millions of light-years away. It could stare at a single galaxy for orbit after orbit, patiently collecting every precious photon of light from those pulsating stars, tracing their rise and fall in brightness with a level of detail that was previously impossible. This ability to create a sharp, clean, and stable light curve for Cepheids in dozens of galaxies was the game-changer. It allowed astronomers to calibrate the period-luminosity relationship with unprecedented fidelity right in the galaxies where Type 1, a supernova, had also been observed. This created a solid, unshakable foundation for the entire cosmic distance ladder. By knowing the exact distance to these calibration galaxies from the Cepheids, scientists could then determine the true intrinsic brightness of the supernova that exploded within them. This turned Type 1, a supernova, from good standard candles into exquisitely precise ones, their wattage now known with a confidence that allowed astronomers to trust them across billions of light years. The results of this decades-long endeavor have placed Hubble at the very heart of the Hubble tension. The telescope's meticulous measurements of the local universe, our cosmic neighborhood, have consistently and confidently pointed to a higher, faster value for the Hubble constant. By building this robust distance ladder, rung by painstaking rung, the teams working with Hubble data have arrived at a value of approximately 73 kilometers per second per megaparsec. This isn't a rough guess, it's a number refined over years, with error bars that have been squeezed smaller and smaller, now sitting at just over 1% uncertainty. This relentless precision is what makes the tension so compelling and so troubling. Hubble isn't just suggesting the universe is expanding quickly, it's stating it with a level of authority that commands attention. The telescope became the gold standard for measuring the present-day expansion rate, and its data represents the most formidable challenge to the predictions emerging from the early universe. Without Hubble's clear-eyed view, we might have dismissed the discrepancy as a measurement error. Instead, the Space Telescope provided the undeniable evidence that we are facing a true cosmic conundrum, a fundamental disagreement between the story of the universe's infancy and the reality of its adulthood, with Hubble itself providing the most precise portrait of the cosmos we live in today. Just as the Hubble Space Telescope began to solidify the data that created the Hubble tension, a new observatory was being designed to see further and more clearly than ever before. The James Webb Space Telescope, launched on Christmas Day 2021, represents a quantum leap in our ability to probe the cosmos. While Hubble primarily sees invisible and ultraviolet light, Webb is an infrared telescope, a design choice that fundamentally changes what we can observe. Infrared light has longer wavelengths than visible light, allowing it to pass through cosmic clouds of gas and dust that would otherwise block our view. It's like trading a regular camera for one with X-ray vision, revealing the hidden universe behind the dusty veils of nebulae and galactic cores. But its infrared vision is also a time machine. As the universe expands, the light from the most distant ancient objects is stretched from its original, shorter wavelengths into the longer, redder part of the spectrum, a phenomenon known as redshift. For the very first galaxies, this stretching is so extreme that their light is only detectable in the infrared. Webb was explicitly built to capture that light, to see the universe not just as it is today, but as it was over 13.5 billion years ago, when the first stars and galaxies were igniting. This unprecedented power makes Webb the great hope for resolving the Hubble tension. Its mission is to attack the problem from multiple angles, providing a suite of new, independent measurements that are free from the potential systematic errors that might be plaguing previous methods. One of its most critical tasks is to refine the cosmic distance ladder from its very foundations. Hubble had a difficult time observing Cepheid variable stars in galaxies that are crowded with dust, as the dust dims and reddens their light, making distance measurements less certain. Webb's infrared eyes cut through that dust with ease. It can observe these crucial cosmic mile markers with phenomenal clarity, even in the most obscured regions of galaxies. By obtaining pristine, high-fidelity measurements of Cepheids in the same galaxies used to calibrate Type 1, a supernova, Webb is effectively checking Hubble's homework, verifying the first rung of the distance ladder with a precision that was previously impossible. If there was a subtle, cumulative error in how we were measuring these stars, Webb is designed to find it, beyond simply double-checking Hubble's work, Webb is pioneering entirely new paths to measure the expansion rate. It is turning its powerful gaze to a different class of stellar lighthouse, the tip of the red giant branch stars. These are ancient, bright stars that all reach the same peak brightness at a specific point in their evolution before they begin to fade. This makes them another excellent standard candle, and they are abundant in all types of galaxies. By measuring distances using these stars independently of the Cepheid variables, Webb provides a completely separate cross-check on the local expansion rate. It's like using two different kinds of rulers to measure the same distance. If they both give you the same answer, your confidence soars. Early results from Webb's observations of these stars have been electrifying, and they are already converging with remarkable precision on the same higher expansion rate measured by the SH0ES team using Hubble. This lends immense credibility to the local measurements and suggests that the tension is not caused by a simple error in our observation of Cepheids. Perhaps most excitingly, Webb is pushing the distance ladder to its absolute limits by directly observing Cepheid variables in galaxies that are hosts to Type 1, a supernova, at much greater distances than Hubble could reliably manage. By building a longer, sturdier ladder that reaches deeper into the cosmos, astronomers can trace the expansion history more directly, bridging the gap between the local universe and the early universe seen in the CMB. Furthermore, Webb's incredible sensitivity is allowing it to observe the earliest supernova ever detected, giving us a new window into the era when dark energy began to dominate over gravity. The James Webb Space Telescope is not just a successor to Hubble. It is a revolutionary instrument that is transforming our cosmic senses from a debate into a data-driven dialogue, bringing us closer than ever to understanding why the universe's two most fundamental stories seem to disagree. This leads us to a deeply counterintuitive fact that often trips people up. If the universe is expanding from a Big Bang, then there must be a central point where it all began, a spot we could, in theory, point to in the sky. It seems logical, but it's completely wrong. The universe has no center. The Big Bang wasn't an explosion in space. It was the rapid expansion of space itself, everywhere at once. To wrap our minds around this, one of the most helpful analogies is the classic raisin bread model. Imagine you're making a loaf of raisin bread, and the unbaked dough, with raisins scattered throughout, represents the early universe. Now, as you place it in the oven, the dough begins to rise. It's not that the raisins are actively crawling through the dough. Rather, the dough itself is expanding, pushing every single raisin away from every other raisin. From the perspective of any one raisin, it would appear as if all the other raisins were moving away from it. The raisin in the top left sees the one in the bottom right receding, and the one in the very center has the exact same view. No single raisin is the center of the expansion. The expansion is a property of the entire loaf. Now, take that concept and scale it up to the entire cosmos. The three-dimensional fabric of space is like that rising dough. Every galaxy is like a raisin embedded within it. As space expands, the distance between every galaxy increases. From our vantage point here in the Milky Way, we observe that nearly all other galaxies are redshifted, meaning they are moving away from us. It would be easy to fall into the trap of thinking we are at the center of this cosmic exodus. But here's the crucial part. An observer in the Andromeda galaxy, or in a galaxy billions of light years away, would see the exact same thing. From their perspective, every other galaxy, including our own Milky Way, would appear to be rushing away from them. There is no privileged center point because the expansion is happening uniformly throughout the entirety of the universe. The very idea of a center requires an edge, a boundary to measure from, but our universe appears to be both without a center and without an edge. It is either infinite in extent, which is a concept that bends the brain, or it is finite but unbounded, like the surface of a balloon, This balloon analogy offers another powerful way to visualize it. Imagine the two-dimensional surface of a partially inflated balloon. Glue a bunch of small dots onto it to represent galaxies. Now, as you blow up the balloon, the surface area stretches. Every single dot moves away from every other dot. An ant living on any one dot would look around and see all the other dots receding. From that ant's two-dimensional perspective, there is no center to the expansion on the surface. The center of the balloon itself exists in the third dimension, a dimension that the ant on the surface cannot perceive or access. In our three-dimensional universe, the expansion we observe is akin to the stretching of that balloon's surface. If there is a higher dimensional center to our cosmic expansion, it is not a location within our observable universe. This is why we say the Big Bang happened everywhere simultaneously. It wasn't that everything was flung outward from a single point into pre-existing space. Rather, space itself began expanding, and every point in the universe was, and still is, part of that initial condition. This fundamental understanding reshapes the entire picture, moving us from a simple cosmic explosion to a much grander and more profound conception of reality, where the very stage upon which the cosmic drama plays out is dynamically and uniformly stretching. This brings us to a concept that is absolutely essential for understanding the true nature of our cosmic home, a distinction that fundamentally separates what we can see from what might actually be out there. We talk about the universe, but what we are really studying, the domain of all our telescopes and measurements, is more accurately called the observable universe. This is not the entire cosmos. It is simply the spherical region of space from which light has had enough time to travel to us since the beginning of time, since the Big Bang. The key ingredient here is not just distance, but time. Light, for all its incredible speed, still takes time to travel, and the universe is only about 13.8 billion years old. This creates a fundamental horizon, a cosmic veil beyond which we cannot see, not because our telescopes aren't powerful enough, but because the light from those more distant regions simply hasn't reached us yet. You can think of it as being in the middle of a vast, foggy ocean. The observable universe is the sphere of clear water around your boat, defined by how far you can see through the fog. The rest of the ocean is still there, but it's hidden from your view. Now, here is where the math becomes truly mind-bending and often leads to confusion. If the universe is 13.8 billion years old, you might logically assume that the radius of the observable universe should be 13.8 billion light-years, giving a diameter of 27.6 billion light-years. That seems straightforward. We look out 13.8 billion light-years in any direction, and that defines the edge of what we can see. But the reality, thanks to the expansion of space itself, is far more spectacular. The most distant objects we can observe, the primordial galaxies seen by the James Webb Space Telescope, and the faint glow of the cosmic microwave background, are not 13.8 billion light-years away. Their light has been traveling for 13.8 billion years to reach us, but during all that time, the space between us and the source of that light has been continuously stretching. By the time the photons finally arrive at our telescopes, the source galaxy has been carried away to a distance that is much, much farther. The current estimated diameter of our observable universe is a staggering 93 billion light-years. That sphere of visibility is immense, containing perhaps 2 trillion galaxies, and it is all defined by that finite speed of light working in concert with the relentless stretching of the cosmic fabric. This leads us to the other, far more mysterious side of the coin, the entire universe, sometimes called the unobservable universe. This encompasses everything that exists, the total cosmos in its full, unimaginable scope, and based on everything we know from the geometry measured in the cosmic microwave background, the entire universe is likely either mind-bogglingly larger than the observable part, or it is truly infinite, extending forever in all directions. The part we can see, the 93 billion light-year sphere that contains all of our science and all of our history, could be just a single grain of sand on an endless beach. The reason we can never know for sure, the reason we are forever confined to our cosmic horizon, goes back to the accelerating expansion driven by dark energy. There is a critical boundary in space where the expansion rate of the universe exceeds the speed of light. This isn't a violation of Einstein's laws. Nothing is moving through space faster than light. Instead, the cumulative stretching of space itself across such vast distances can cause the separation between 2 points to increase at a rate that light can never overcome. Imagine a lonely galaxy located just beyond our current observational horizon. It is so far away that the space between us and it is expanding at a rate exactly equal to the speed of light. The photons it emits in our direction are like a swimmer trying to cross a river that is flowing outward faster than they can swim. They make no headway whatsoever. They are stuck, forever trapped by the stretching of space. Now consider a galaxy even farther away, where the space between us is expanding faster than light. Any light it sends out is not just slowed down, it is actually being carried away from us, like a swimmer in a current so strong they are swept downstream, moving farther from their destination with every stroke. This means there are entire regions of the cosmos, potentially containing countless galaxies, stars, and maybe even other forms of life, whose light or any other signal will simply never, ever reach us. They are causally disconnected from our little pocket of the universe, forever separated from us by an impassable gulf created by the accelerating expansion. This isn't a temporary barrier. It is a permanent and growing isolation, ensuring that our observable universe will only ever be a tiny, isolated island in a much vaster and ultimately unknowable cosmic ocean. To truly understand the strange acceleration we measure today, we have to rewind the cosmic clock not just billions of years, but to the very first fraction of a second after the Big Bang, where an even more dramatic and profound expansion event occurred. This was the era of cosmic inflation, a concept that sounds like science fiction, but is a cornerstone of modern cosmology. Imagine the infant universe, not even a second old, existing as a seething, chaotic, and incredibly dense quantum foam. At this moment, something extraordinary happened. A peculiar form of energy, a field dubbed the inflaton field, came to dominate the cosmos. This field possessed a bizarre property. It generated a powerful, repulsive gravity, causing the fabric of space itself to expand at an exponential rate that is almost impossible to comprehend. The numbers involved are so vast they defy intuition. In a time span so short, it makes a nanosecond seem long, perhaps from 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds. The universe doubled in size, and then doubled again, and again, over and over, for perhaps 80 or 100 doublings. Think of it like this. You have a single marble, then in one doubling you have 2, in another you have 4, then 8, and so on. By the time you have doubled 100 times, you have a number of marbles so vast it would fill a sphere larger than our entire observable universe. That's the explosive, hyper-fast growth we are talking about. This inflationary growth spurt did 2 critical things that shaped the cosmos we inhabit. First, it took whatever tiny, primordial patch of the universe existed and stretched it to an enormous size, effectively ironing out any wrinkles or curvature. This explains why the universe we see today, on its largest scales, is so remarkably flat and uniform. No matter which direction we look, the cosmic microwave background has almost exactly the same temperature, a fact that was deeply puzzling before inflation provided the explanation. The entire observable universe was once a tiny, causally connected region that was stretched to cosmic proportions, smoothing everything out in the process. Second, and perhaps even more importantly, inflation planted the very seeds for all the structure we see around us. The quantum world is inherently uncertain, a turbulent sea of tiny fluctuations. During the ultra-rapid stretching of inflation, these minuscule quantum jitters, fluctuations in the inflated field itself, were magnified to astronomical scales. Think of a tiny, microscopic ripple on the surface of a balloon. If you suddenly inflate that balloon to the size of the Earth, that tiny ripple becomes a massive, continent-sized wave. In the same way, the infinitesimal quantum fluctuations from the universe's first instance were stretched into tiny differences in density, slightly hotter spots and slightly colder spots that were imprinted across the cosmos. These minute variations became the gravitational seeds around which matter would later clump, eventually giving rise to the magnificent cosmic web of galaxies, clusters, and voids. Without these quantum seeds, stretched and frozen into the fabric of the universe by inflation, the cosmos would have remained a featureless, uniform soup, and stars, planets, and life would never have formed. Now, let's connect this ancient event to the mystery we grapple with today. The current accelerated expansion, driven by dark energy, is profoundly different from inflation in both scale and cause, but it shares a fundamental similarity. It is also an expansion of space, powered by a form of energy with repulsive gravity. The key difference lies in the intensity and timing. Cosmic inflation was an unimaginably violent, exponential burst that lasted for a mere flicker of time and increased the size of the universe by a factor of at least 10 to the 26. In contrast, the acceleration we see today is a far gentler, slower, and linear process that has been ongoing for billions of years and is only now becoming the dominant force. Dark energy is like a faint, persistent whisper, while inflation was a cosmic shout of unimaginable power. Yet, the parallel is striking enough for cosmologists to wonder if dark energy could be a vastly diluted, modern-day remnant of that initial inflationary field, or perhaps a different manifestation of a similar underlying mechanism. The current acceleration can be seen as a faint, cosmic echo of that initial, spectacular growth spurt, a reminder that the universe's capacity for rapid, repulsive expansion is not a one-time event, but a fundamental feature woven into its very nature from the very beginning. But how can we possibly know that the universe looks the same everywhere when we are stuck in our own tiny corner of it? This question leads us to one of the most profound and necessary assumptions in all of science, a foundational pillar of modern cosmology known as the cosmological principle. In its simplest form, this principle makes two bold assertions about the universe on its very largest scales. First, it states that the universe is homogeneous. This doesn't mean every single cubic patch of space contains an identical number of galaxies. That would be ridiculous, given the vast voids and dense clusters we see. Instead, it means that if you were to take a cosmic-sized scoop of the universe, a cube measuring, say, 1 billion light-years on each side, it would contain roughly the same amount of matter and energy, on average, no matter where in the universe you took that scoop from. The overall density and texture of the cosmos would be uniform. The second part of the principle states that the universe is isotropic. This means it looks the same in every direction you look. From our vantage point, we don't see a wall of galaxies in one direction and an empty void in another. The grand distribution of galaxies and clusters appears statistically similar, no matter which window we peer out of. Now, why would scientists make such a grand assumption? Because without it, we couldn't do cosmology at all. The cosmological principle is the ultimate statement of cosmic humility. It declares that we do not occupy a special, privileged place in the universe. Our position on Earth in the solar system, in the Milky Way galaxy, is utterly typical and unremarkable. This idea, known as the Copernican principle, is the philosophical heart of the cosmological principle. It is the direct successor to the revolutions of Copernicus, who showed Earth was not the center of the solar system, and Hubble, who showed the Milky Way was not the center of the universe. If we were in some unique, central location, then all our observations would be skewed, and we could never extrapolate the local laws of physics to the cosmos at large. The cosmological principle gives us the confidence to believe that the physics we discover here in our laboratories applies with equal force in a galaxy 10 billion light-years away. It is the bedrock upon which we build our models of the universe's history, from the Big Bang to its present-day acceleration. The most stunning and direct evidence for this principle comes from the very expansion we've been discussing. Hubble's law, the observation that a galaxy's recessional velocity is directly proportional to its distance, is a perfect, natural consequence of a homogeneous and isotropic universe that is uniformly expanding. Think back to the rising raisin bread dough. From the perspective of any single raisin, all the other raisins are moving away, and the farther ones are receding faster. This relationship only holds true if the dough is rising evenly. If the dough had a lumpy, uneven rise, some raisins would be moving in strange, unpredictable ways. The beautiful, clean, linear relationship that Edwin Hubble discovered in his velocity-distance plot is the observational proof that the expansion is uniform, which in turn strongly implies that the underlying universe is homogeneous and isotropic on those grand scales. It tells us that the cosmic fabric is stretching in the same way everywhere, a symphony of expansion where every point is, in a sense, the center of its own observable universe. Further, incredibly powerful confirmation comes from the oldest light we can see, the cosmic microwave background radiation. When we look at the map of this afterglow from the Planck satellite, we are seeing the universe as it was at a mere 380,000 years old, and it is stunningly smooth. The temperature fluctuations across the entire sky are minuscule, varying by only about 1 part in 100,000. This incredible uniformity is exactly what the cosmological principle predicts for the early universe. Those tiny ripples are the seeds of future structure, but the overall canvas is remarkably homogeneous and isotropic. We see the same pattern of hot and cold spots, whether we look toward the constellation Orion or in the exact opposite direction. This is not what we would expect if we were located in some special, atypical region. It is what we would see from any average point in a universe that adheres to this fundamental principle. The cosmological principle is not just a convenient assumption. It is a hypothesis that has been tested and validated time and again by our most precise observations of the cosmos, allowing us to speak with confidence about the nature of the entire universe from our tiny and wonderfully ordinary perch within it. This brings us to a name that seems to create a lot of confusion, the Hubble constant itself. That word constant is a bit of a misnomer, and it's one that often leads to a misunderstanding of what this crucial number actually represents. In the context of Hubble's law, what is constant is the relationship, the direct proportionality between a galaxy's distance and its recessional velocity, right here and right now. The number that describes that proportionality, however, is not fixed for all of time. A more accurate, though less catchy, name might be the Hubble parameter. What we are measuring today, the 70 or so kilometers per second per megaparsec, is simply the current value of this evolving parameter. It is the universe's present-day expansion rate, a single frame in a cosmic movie that has been playing for 13.8 billion years. The true goal of cosmology is not just to pin down this one number, but to understand the entire film, to map out how this expansion rate has changed dramatically from the universe's first frantic moments to the accelerating era we find ourselves in today. To appreciate just how dramatic this evolution has been, we need to rewind the clock all the way back to the era of cosmic inflation. If you think the current expansion is fast, it is an absolute crawl compared to the hyperdrive growth spurt that occurred in the universe's first fraction of a second. During inflation, the Hubble constant was not just large, it was astronomically, unimaginably enormous. The value was likely about 55 orders of magnitude larger than it is today. That's a number with 55 zeros after it. This incomprehensible rate was driven by the potent energy of the inflatoned field, which generated such powerful repulsive gravity that it stretched the fabric of space to an almost instantaneous, exponential degree. This wasn't a gentle, steady expansion. It was a violent, explosive burst that set the stage for everything to come. After inflation ended, that immense energy decayed, transforming into the hot soup of particles and radiation that would fuel the Big Bang. From that point on, the story of the Hubble parameter became one of a long, gradual slowdown, governed by the relentless pull of gravity. For billions of years, the collective gravitational attraction of all the matter and radiation in the universe, the dark matter, the stars, the galaxies, the photons, was acting as a cosmic brake, tirelessly working to slow the expansion down. Think of it like throwing a ball straight up into the air. As soon as it leaves your hand, Earth's gravity begins to pull on it, continuously slowing its ascent. In the same way, the universe's expansion has been decelerating for most of its history. The early universe was expanding with incredible vigor, but gravity was constantly tugging on the reins, causing the Hubble value to decrease over time. If we had been there to measure it just a few billion years after the Big Bang, we would have found a Hubble constant significantly higher than the value we measure in our local universe today. This long cosmic deceleration continued until about 5 billion years ago, when everything changed. This is the pivotal moment when the density of matter, which had been thinning out as the universe expanded, dropped below the constant energy density of dark energy. It was the moment dark energy won the cosmic tug-of-war. Once its repulsive push became the dominant force, the expansion of the universe didn't just stop slowing down, it began to speed up again. The Hubble constant, which had been on a steady decline for 9 billion years, bottomed out and began a very slow increase. It's as if that ball we threw in the air, instead of slowing to a stop and falling back, suddenly encountered a mysterious upward wind that started pushing it faster and faster into the sky. So, the history of the Hubble value is a story of 3 distinct acts: an initial, unimaginably high value during inflation, a long epoch of deceleration dominated by gravity, and our current era, a reacceleration driven by the enigmatic force of dark energy. The number we work so hard to measure today is merely a single data point on this grand and complex curve. Looking even deeper into the cosmos than supernova or Cepheid stars requires a beacon of truly staggering power, and nature has provided us with the most energetic objects in the known universe, quasars. The name itself stands for quasi-stellar radio source, a label given in the 1960s when these points of light appeared star-like in telescopes but emitted bizarre and powerful radio waves. We now understand quasars to be the intensely bright, active hearts of distant galaxies, powered by one of the most extreme engines imaginable, a supermassive black hole in the midst of a cosmic feast. At the center of a young galaxy, a black hole with a mass millions or even billions of times that of our Sun is surrounded by a vast, swirling disk of gas and dust. As this material spirals inward, pulled by the black hole's immense gravity, it is heated to millions of degrees, causing it to glow with a ferocious brightness that can outshine the entire galaxy that hosts it. This accretion disk becomes a brilliant lighthouse, and in some cases, the black hole also shoots out colossal jets of charged particles traveling at nearly the speed of light. The combined effect is a single object so luminous that we can detect it from the very edge of the observable universe, from a time when the cosmos was less than 1 billion years old. This makes quasars an irresistible tool for cosmologists trying to measure the universe's expansion history. When we observe the light from a quasar, we are not just measuring a single point of light. We are collecting a rich spectrum that tells a detailed story. The light has traveled for billions of years through the expanding cosmos, and along its journey, it has passed through vast clouds of intergalactic gas, primarily neutral hydrogen. These clouds absorb specific wavelengths of the quasar's light, creating a dense forest of dark lines in the spectrum, known as the Lyman alpha forest. This forest is not random. The pattern of absorption lines is directly sculpted by the large-scale structure of the universe, the cosmic web of filaments and voids that the light had to navigate. By analyzing this complex fingerprint, scientists can do something remarkable. They can map the distribution of matter along the line of sight to the quasar and measure the precise amount by which the universe has stretched since that light began its journey. It's like being able to count every single tree in a vast, ancient forest from thousands of miles away, simply by analyzing the pattern of shadows it casts. Because quasars are visible from such immense distances and early cosmic times, they allow us to probe the expansion rate during a crucial period, the era when dark energy was beginning to take over from matter as the dominant component of the universe. By measuring the redshifts and distances of thousands of quasars spread across different cosmic epochs, we can construct a timeline of the Hubble parameter, effectively charting how the expansion rate has changed over the last 12 billion years. This provides a powerful, independent check on the expansion history we get from supernovae. It's a different methodology with its own set of challenges, but it converges on the same incredible story. The data from quasars confirms that the universe's expansion decelerated for its first 9 billion years, exactly as expected from the gravitational pull of dark matter and normal matter. Then, around 5 billion years ago, the expansion began to accelerate, just as the supernova data showed. This independent confirmation from quasars gives us tremendous confidence that the acceleration is a real, physical phenomenon and not some systematic error unique to one type of observation. Perhaps the most exciting potential of quasars lies in their ability to test whether dark energy is truly constant. The standard cosmological constant model makes a very specific prediction for how the expansion rate should have evolved during this transition period from deceleration to acceleration. By using quasars to measure the Hubble parameter at multiple, finely sliced intervals of cosmic time, astronomers can look for any subtle deviations from this prediction. If dark energy were instead a dynamic force that has been changing in strength, a concept known as quintessence, it would leave a distinct signature in the expansion history traced by these ancient beacons. While current data from quasar surveys like the Sloan Digital Sky Survey are incredibly precise, they still agree with a simple, constant dark energy. However, the quest continues. Next-generation telescopes and surveys plan to map hundreds of thousands of quasars, building an exquisitely detailed movie of the universe's expansion. These cosmic lighthouses, shining from an era of violent galactic youth, may yet hold the key to revealing the true, and perhaps evolving, nature of the mysterious force that dictates our cosmic fate. But to truly appreciate how we can map the cosmos with sound, we need to journey back to that primal cosmic sea, the universe before it was even 380,000 years old. At this time, the cosmos was a scorching, opaque plasma, a thick soup of photons, electrons, and atomic nuclei. In this seething environment, gravity was constantly trying to pull the matter together into denser clumps. But it faced a formidable opponent, the intense pressure of the radiation. Photons were so densely packed that they couldn't travel far without slamming into an electron, creating a constant, violent push against gravity's pull. This epic tug of war between gravity's relentless crush and radiation's powerful outward pressure set the entire universe ringing. It generated powerful, spherical pressure waves that radiated outwards through the plasma cosmic sound waves traveling at a significant fraction of the speed of light, about 2/3 of light speed, to be precise. The entire infant universe was literally humming, a cosmic symphony on a scale so vast it's almost impossible to comprehend. These sound waves, however, could not travel forever. They were entirely dependent on the tightly coupled dance between photons and electrons. The moment the universe expanded and cooled enough for atoms to form, a pivotal event called recombination, the music suddenly stopped. Electrons were captured by protons to form neutral hydrogen and helium atoms. For the photons, this was like a prison break. They were suddenly freed, no longer constantly colliding with electrons, and could stream across the universe, becoming the cosmic microwave background we detect today. For the sound waves, this was the end of the line. The moment the photons decoupled, the pressure that was driving the waves vanished. The waves instantly froze in place, their outermost edge forever marking the maximum distance a sound wave could have traveled from any initial density fluctuation. This distance is known as the sound horizon, and it became a permanent, fixed standard ruler etched into the very fabric of the cosmos at that precise moment. The beauty of this sound horizon is that we know its exact physical size with incredible precision. From our understanding of the physics of the early universe, its temperature, density, and composition, we can calculate that this frozen wave front had stretched to a diameter of about 500,000 light-years by the time of recombination. This is not an estimate. It's a fundamental prediction from our well-tested models of particle physics and cosmology. This scale was then imprinted onto the universe in two powerful and independent ways. First, it appears in the cosmic microwave background as a very specific, dominant size for the hot and cold spots we see in the Planck satellite map. Those spots are not random. Their characteristic angular size is a direct reflection of the physical size of the sound horizon projected onto the sky. Second, and just as importantly, this same scale was stamped into the distribution of the matter itself. The spherical sound waves created a subtle preference for galaxies to form at a specific separation. The radius of those ancient waves, now stretched by 13.8 billion years of cosmic expansion to nearly 500 million light-years. This is the magic of baryon acoustic oscillations as a cosmic tool. We have a standard ruler whose true length we know from first principles. We don't need to calibrate it with Cepheid variables or supernovae. It is a fundamental gift from the physics of the early universe. To measure the expansion history, we simply find this ruler at different cosmic epochs and see how its apparent size has changed. When we look at the distribution of relatively nearby galaxies in massive surveys, we can statistically detect that they are more likely to be separated by this specific scale. We then look much deeper into space, at populations of extremely ancient galaxies, and measure the apparent size of the ruler there. Because the universe has expanded more along the line of sight to these more distant objects, the ruler appears larger to us. By comparing the known true size to the apparent size at different distances, we can chart exactly how the universe has stretched over billions of years. This provides a completely geometric, independent confirmation of the expansion, and its results powerfully agree with the supernova data, cementing the reality of cosmic acceleration. However, when this pristine early universe ruler is used to predict the current expansion rate, it points firmly toward the lower value championed by the Planck satellite, directly fueling the Hubble tension and suggesting that the simple story we've been telling about the cosmos might be missing a crucial, hidden chapter. The greatest mysteries in science rarely remain unsolved for long, not because the answers become easy, but because our tools for seeking them grow ever more powerful. The profound Hubble tension and the enigma of dark energy are no different. While today's data presents a compelling crisis, the next generation of astronomical observatories is already poised to launch, designed with the explicit goal of turning this era of beautiful confusion into one of revolutionary clarity. Two missions in particular stand as giants on the horizon, ready to map the cosmos with a scope and precision that was unimaginable just a generation ago, turning the faint whispers of dark energy into a clear, measurable signal. First, soaring through space right now is the European Space Agency's Euclid telescope. Launched in July 2023, Euclid is a unique and powerful instrument built for a single, monumental purpose: to create the most extensive and accurate three-dimensional map of the universe ever made. It will achieve this not by staring at a tiny patch of sky, but by surveying a staggering 1/3 of the entire heavens, observing billions of galaxies out to distances of 10 billion light-years. Euclid's strategy is twofold, using two powerful, independent methods to corner dark energy. The first is weak gravitational lensing. As light from distant galaxies travels toward us, it is subtly distorted and sheared by the gravitational pull of all the matter, both visible and dark, it passes along the way. Euclid will measure these tiny, characteristic distortions in the shapes of billions of galaxies. By tracking how this cosmic shear changes across different cosmic epochs, scientists can trace the growth of the cosmic web over time, which is exquisitely sensitive to the push of dark energy and the pull of dark matter. It's like watching a shadow play on a wall. To understand the objects casting the shadows, the distortions in the light reveal the distribution of the invisible mass-warping spacetime itself. Euclid's second method is a high-precision measurement of baryon acoustic oscillations, the frozen sound waves from the early universe. By pinpointing the locations of tens of millions of galaxies and measuring their preferred separation across vast cosmic distances, Euclid will chart the expansion history of the universe with phenomenal accuracy. This geometric measurement is completely independent of the supernova distance ladder, providing a crucial cross-check on the Hubble constant. What makes Euclid so potent is its ability to perform these two measurements simultaneously on the same colossal dataset. By combining the growth of structure from weak lensing with the expansion history from baryon acoustic oscillations, Euclid can test whether dark energy behaves exactly like Einstein's simple cosmological constant, or if it shows signs of being a dynamic, evolving force. The telescope's data will either solidify our standard model or reveal the cracks that demand entirely new physics. Meanwhile, from a mountaintop in Chile, another behemoth is preparing to join the hunt. The Vera C. Rubin Observatory, with its groundbreaking legacy survey of space and time, or LSST, will take a different yet equally powerful approach. While Euclid is a dedicated space mission for precision cosmology, Rubin is a ground-based survey of unparalleled speed and breadth. Its primary mirror is enormous, and its camera is the largest digital camera ever built, containing over 3.2 billion pixels. Every few nights, it will capture an entire panorama of the southern sky, and over its 10-year mission, it will do this more than 800 times, creating an unimaginably vast cosmic movie. This dynamic view of the heavens allows Rubin to excel in an area where other telescopes simply cannot compete, finding transient events, things that change in the night sky. This makes it a supernova discovery machine. Rubin's LSST is expected to find millions of Type 1a supernova, dwarfing all previous supernova surveys combined. These aren't just numbers. Each supernova is a data point in the expansion history of the universe. With this colossal statistical sample, astronomers will be able to trace the transition from cosmic deceleration to acceleration with a smooth, unbroken curve, eliminating the uncertainties that come from smaller datasets. Furthermore, by observing these supernovae at such immense distances, scientists can test whether their properties have changed over cosmic time, addressing a key potential systematic error in the original acceleration discovery. Beyond supernova, Rubin will also perform its own incredibly detailed weak lensing and galaxy clustering surveys, mapping the distribution of matter and the evolution of the cosmic web with a statistical power that is simply overwhelming. The synergy between Euclid and Rubin is what makes this upcoming era so thrilling. Euclid, from its pristine vantage point in space, will provide exquisitely sharp, deep images for precision measurements. Rubin, from the ground, will provide the colossal volume and time domain coverage. Together, they will cross-calibrate each other's findings, ruling out instrumental errors, and providing a combined dataset so powerful and robust that it will either definitively resolve the Hubble tension or reveal, beyond any doubt, that our current understanding of the cosmos requires a fundamental rewrite. These are not just telescopes, they are engines of discovery, built to answer the most pressing question of our cosmic age. So after this incredible journey through 30 facts, from the first tentative measurements of Edwin Hubble to the terrifying possibilities of a Big Rip, we are left with a single, inescapable conclusion that is as humbling as it is awe-inspiring. We have pieced together a story of cosmic evolution that stretches across 13.8 billion years, a narrative written in the light of dying stars, the echoes of primordial sound waves, and the silent geometry of bent spacetime. We have given names to our ignorance, dark matter, and dark energy, and in doing so, have mapped the very edges of our understanding. But what does this grand cosmic saga, this tale of a runaway universe, ultimately mean for us, the temporary inhabitants of a small, rocky world? The answer lies not just in the physics, but in the profound philosophical shift this knowledge forces upon us. First and foremost, it is a lesson in cosmic humility. Every single discovery we have discussed systematically removes us from a position of privilege in the universe. We are not at the center of anything. Our planet is a speck orbiting an average star, one of perhaps hundreds of billions in our galaxy. Our galaxy, the Milky Way, is itself just one of an estimated 2 trillion galaxies in the observable universe, each a sprawling island of billions of stars. And now we know that all these galaxies are mere flotsam on the tide of expanding space, carried ever farther apart by a force we cannot see or touch. We live in a universe that is not only unimaginably vast, but also fundamentally transient, evolving toward a future of cold, dark isolation. In the grand timeline of the cosmos, the entire history of human civilization is less than a blink of an eye, a fleeting moment in the multi-billion-year narrative of cosmic acceleration. This perspective can feel crushing, reducing our individual lives and struggles to utter insignificance against the colossal backdrop of an expanding, accelerating cosmos. And yet, there is a second, more powerful and defiant truth buried within that same humbling reality. Consider the sheer improbability of our situation. We are collections of atoms, the remnants of stars that lived and died long ago, that have somehow organized themselves into beings capable of consciousness, curiosity, and reason. On our tiny world, with our limited senses, we have managed to do something extraordinary. We have built instruments that can see back to the very first light of the universe. We have devised mathematics that can describe the curvature of space-time and the quantum froth of the vacuum. We have sent robotic emissaries to other worlds and telescopes into the void to capture photons that have been traveling for over 13 billion years to reach us. Our tiny minds, confined to a pale blue dot in a forgotten corner of a typical galaxy, have successfully decoded the life story of the entire cosmos. We have deduced the Big Bang, measured the expansion, and uncovered the acceleration. We have peered into the abyss of deep time and the terrifying vastness of space, and we have not looked away. This is not insignificance. This is a triumph of epic proportions. This leaves us with a beautiful and poignant duality. On one hand, we are cosmically insignificant, temporary residents of a universe that is largely made of stuff we do not understand, racing toward a future that holds no place for us. On the other hand, we are the universe's way of becoming self-aware, the means by which the cosmos can look back upon itself, contemplate its own origins, and wonder at its own fate. The same physical laws that govern the spin of a galaxy and the nuclear furnace of a star also operate within our own bodies and power our own thoughts. We are not separate from the universe. We are a conscious, thinking part of it. The accelerating expansion and the mystery of dark energy are not just abstract puzzles for scientists. They are part of our own extended story. The fact that we can even formulate the questions, that we can feel a sense of awe and terror in the face of this immense narrative, is itself a kind of miracle. It means that in this cold, vast, and seemingly indifferent cosmos, a spark of understanding has flickered to life, and for a brief moment, the universe knows itself. And so we arrive at the end of our journey, standing at the edge of a mystery that is both humbling and exhilarating. The grand takeaway is as clear as it is baffling. Our universe is not just expanding. It is in a state of runaway acceleration, pushed ever faster by a force we call dark energy. This isn't a gentle drift, but a fundamental, relentless stretching of the cosmic fabric itself. We've traced this astonishing discovery from the painstaking observations of Edwin Hubble to the brilliant Nobel Prize-winning work on distant supernovae. We've seen how this acceleration dictates a future of growing isolation and cold, a cosmic destiny that seems almost written in stone. Yet, for all we have learned, the most profound questions remain unanswered. We have given this force a name, but its true nature is one of the greatest enigmas in all of science. This brings us to the thrilling present moment, defined by the Hubble tension. This isn't a sign of failure in our scientific methods, but rather a beacon pointing toward the next great leap in our understanding. The persistent disagreement between the early universe's baby picture and the local universe's current expansion rate is not a problem to be solved. It is a clue to be followed. It strongly suggests that our current model of cosmology, for all its incredible predictive power, is incomplete. Perhaps dark energy is not a constant vacuum energy, but something that evolves over time, a dynamic field known as quintessence. Maybe there are exotic, unknown particles from the universe's first moments that have subtly altered its evolution. Or, most radically of all, it could be a signal that our understanding of gravity itself, Einstein's magnificent theory of general relativity, needs to be revised on the largest cosmic scales. This tension is the universe's way of whispering to us that there is more to the story, that a deeper layer of physics is waiting to be uncovered. So, we are left not with a neat conclusion, but with an invitation, an open door to the future of discovery. The greatest scientific breakthroughs often come from precisely these kinds of stubborn discrepancies, the data points that refuse to fit the established narrative. With next-generation observatories like the James Webb Space Telescope, the Euclid mission, and the Vera C. Rubin Observatory now scanning the heavens, we are arming ourselves with unprecedented tools to interrogate the cosmos. They will measure the expansion history with staggering precision, map the dark matter web in exquisite detail, and search for any subtle evolution in the strength of dark energy. We are on the verge of a new era of cosmic cartography, one that promises to either reconcile this tension or reveal a universe stranger than we ever imagined. The universe is telling us a story, and we are only just beginning to learn how to listen. What do you think is the solution to the great expansion rate mystery? Let us know your theories in the comments below. And don't forget to subscribe for more journeys into the cosmos. But here's a truly wonderful part of this story. You don't need a PhD or access to a multi-billion-dollar space telescope to contribute to this grand cosmic quest. In fact, some of the most important data analysis in modern astronomy is being done by people just like you, sitting at home with a computer or even a smartphone. This is the world of citizen science, a collaborative movement where professional researchers invite the global public to help sift through the mountains of data that modern observatories produce. When a telescope like the Vera C. Rubin Observatory begins its work, it won't just take a few pretty pictures. It will generate a veritable tidal wave of information, capturing images of billions of galaxies and stars every single night. There are simply not enough professional astronomers in the world to look at every single one of those galaxies and classify them. The human brain, however, is still exceptionally good at pattern recognition, often spotting subtle details and anomalies that even the most sophisticated computer algorithms might miss. This is where platforms like Zooniverse come in. Zooniverse is the world's largest and most popular platform for people-powered research, hosting dozens of projects where anyone with an internet connection can become a cosmic explorer. One of its flagship projects is Galaxy Zoo, which has been running for over 15 years. In Galaxy Zoo, volunteers are presented with a stunning image of a galaxy taken by a telescope like Hubble or the Sloan Digital Sky Survey. The task is beautifully simple. Just look at the galaxy and answer a few basic questions about its shape. Is it a smooth, featureless ellipse? Does it have spiral arms? Is it an irregular, messy blob? Or is there something strange happening, like a possible collision with another galaxy? Each classification you provide is a vital data point that helps astronomers understand how galaxies form and evolve. The collective power of millions of these classifications from hundreds of thousands of volunteers has led to a wealth of scientific discoveries, including the identification of entirely new classes of galaxies and the study of how a galaxy's shape relates to its environment in the cosmic web. The impact of this public participation goes far beyond just cataloging. Consider the story of Hannes Voorwerp, a Dutch schoolteacher named Hanny van Arkel, who was classifying galaxies on Galaxy Zoo in 2007 when she noticed a strange, glowing green blob of gas near a spiral galaxy. It was unlike anything the professional astronomers had ever seen. Her curiosity and sharp eyes led to a full-scale scientific investigation, and Hannes Voorwerp is now a recognized astronomical phenomenon, a quasar ionization echo, where a dying quasar lit up a massive intergalactic gas cloud long after the quasar itself had faded. This remarkable discovery, made by a citizen scientist, was published in a major scientific journal and has spawned its own field of study. It's a perfect example of how a curious person, given access to real data, can make a genuine and lasting contribution to our understanding of the universe. By participating in a project like this, you become part of the scientific process itself. The classifications you make are used by researchers to train machine learning algorithms to identify the most interesting targets for follow-up observations with major telescopes and to build statistical models of the universe's structure. Every click is a small but meaningful piece in the grand puzzle of cosmology, in the context of the universe's expansion. Helping to classify galaxies contributes to our maps of the large-scale structure, which are essential for measuring phenomena like baryon acoustic oscillations and understanding the distribution of dark matter. While you might not be calculating the Hubble constant directly, you are helping to build the foundational maps that make those precise measurements possible. It's a powerful and empowering thought. The next big clue in the mystery of dark energy or the resolution to the Hubble tension could, in some small way, begin with you, an everyday explorer, noticing something wonderful in the deep sky.